mission of Professor Dr. Rajesh Kumar sir. Sir, can we start the session, sir?
Yes, please, let's start it.
Let us first introduce about Dr. Rajesh Kumar sir. It gives me the immense to introduce you all about the eminent expert. Our today's technical session for Dr. Rajesh Kumar sir. Professor Rajesh Kumar working as a professor with the Department of Engineering, MNIT Jaipur. Received his B degree from NIT Kurukshetra, Tech degree system and PhD degree in Intelligent System, MNIT Jaipur. He was postdoctorate research fellow, Department of Electrical and Computer Engineering at National University of Singapore from 2009 to 11. Dr. Kumar has published over 450 research articles, 20 PhD and more than 30 theses, 12 patents in his name. He received 3 Academy Awards and 12 Best Paper Awards, Best Thesis Award, 4 Professional Awards and 25 Student Awards. He has received the Career Awards for Young Teachers in 2002 from Government of India. On 12 editorial boards, he is an associate editor of IEEE's Industrial Electronics Technology News, associate editor SWAM and Evolutionary Computation Elsewhere, associate editor IET Renewable and Power Generation. Head IET Power Electronics, associate editor International Journal of Inspired Computing, deputy editor in chief EAI Transaction and on Intelligence Technology, IET. He is a senior member USA, fellow IET UK, fellow IE India, fellow IETE, life member CSI, senior member IEG, and life member IST. His research interests focus on intelligent system, machine intelligence, power management, smart grid, and robotics. With this brief introduction, I would like to hand over the session to Dr. Rajesh Kumar sir for further proceeding. So over to you, sir.
I'm sharing the screen. Let me know it's
Yes, sir.
visible to everyone.
Yes, sir.
It's visible.
Yeah, okay. And I'm audible to everyone, right?
Yes, sir.
Okay, so good morning to all my faculty colleagues and research scholars who are here for this today's discussion. And the agenda I have taken for today's 2 hour discussion is on multi-agent systems, and the problem I've taken microgrid as a case study, which I'll discuss towards the end of the presentation. So the flow of talk will be, I will try to understand what is a multi-agent system, what are the components of a multi-agent system, how it help in distributed control, so that we can apply in control system also. Also, we try to understand how it can be applied to other research domains. Then we discuss on like how we can make it multi-agent, and then I'll take 2-3 case studies related to electrical engineering. And at the end, I'll take questions from your side so that we can have more discussion on the topic itself. Okay, taking it further, when we talk about microgrids and smart systems and all these things, so this is what we are expecting in microgrid. Normally, like we are looking for automation in microgrids. What we want, everything should be displayed on our screen. That means like how much is the power generated at what point, how much is the consumption. In future, we are looking towards electric vehicles. So Mm, the, the, the interesting concept will be there that electrical vehicle can be a source and can be a sink. So how they are behaving at a different nodes, or sitting in a one room or control room, can we control the room things from one center, something like that. Even we are looking for, okay, what are the load profiles, thermal profiles, temperature and weather conditions, so that we can interrelate these things with electrical quantities or load quantities, or help in predictions and help in calculation of the different loads. And at the same time, we are looking for something like, okay, as kind of smart meters, because they provide a different level of information exchange. So many things are happening towards all around in as in electrical engineering as such, but we can see that they are coupled with each other, because not only this one is application domain only, but the things which are happening here, they're full of electronics, computers, and IT sector as such. So these things are mixing, and then we can say that, okay, we are moving towards a domain of intelligent systems, and one of them is a smart grid, basically. So smart grid, basically the consumers are here. Okay, let me check the pointer if it is there. So we can see here the consumers are here. So they want each and everything on their mobile phones or laptops or palm tops or something like that, so that they can visualize the things in a most appropriate manner and what they are interested in, depending upon their requirement. So at the back end, we have all management things will work, like home energy management, load management, storage management, renewable integration, electric vehicle management, and other quantities also. So the front end is the screen where person can see that, okay, how much is the power he is consuming, which equipment is consuming, what is the quality of the power, and then how much is the cost in the real time frame, and all those things. And at the same time, the consumer expect that, okay, these things can and these things are in the optimized manner, optimized in the sense that the only objective, most of the time, the objective of the consumer is to pay less for good quality of power. And the back end, then we need all these things to work on, that how to manage the energy at his home and other factors there. And then this one is the middle layer, and the basic layer is your electrical kind of systems, which are right now they are there, so they are working. And then how these electrical equipments can be further automatized, or and then they can be used in most appropriate manner. So a lot of things they are merged, many technologies are merged to realize this type of the scenarios. Okay. So actually, the things comes from this slide. You can see the change in the revolution appears from here. We have two types of infrastructure. One is your electrical infrastructure, and second one is your communication infrastructure. Intelligence will talk later on. So in electrical infrastructure, we have generation, and then we have transmission, and then the distribution, and then the power is coming to home. There is some kind of analogy in communication infrastructure also, so that we have transmission through satellites, and then we have LAN, WAN, HAN, and all these things comes, and finally we have internet data on our laptops or mobile phones. The difference between these two structures, this one and this one, in electrical network, we have power level very high, and the uh, flow is only 50 or 60 hertz, depending upon the topologies or countries. In the second case, the power level is very low, but the data transmission is in Gbps and even more than that. So the idea comes in is like, okay, when these two things they combine with each other, and then can we have one system where we can use the benefit of one, and then to compensate the things for other, or if we use the benefit of one and to make the second system more reliable, more advanced. So this one is basically comes at for the smart grid. You can say the backbone is the communication system where the data flow very fast, And since the data flow very fast, so we have time to take certain kind of decisions, and that will help us in making our system more reliable and robust there. And because of this, you can see a lot of things appears into the domain, like dynamic pricing, dynamic demand responses, self-healing systems, asset management, real-time simulations, and all these things, because the information is shared very fast. And since we have certain, we can think of like, okay, we have certain time there, because information is very fast and we have lot and lot of data. So we can say, we can think of continuous optimizing the things, or the thing, assets we have, or variables we have. And so that finally when you integrate all these together, the response is intelligent. So this is just a kind of a thought, like, okay, how the new things comes in. So even our existing grids, we put it on the backbone of communication system. We are making a bit smart, and then if we use automated, or the if we are in a position to replace our uh, some components or the devices with uh, communication enabled systems, or so then we can say that, yes, we are moving much towards a intelligent system, because what we are looking is the system in total behaves an intelligent, in most intelligent way. So this is what we can think of, like, in future what it will be like, that we have so many things which are right now, they are already being placed, and they are being used in developed countries. Developing countries, still they are in the process of implementing these things. So we have smart homes, and where we have smart meters, microgrid managers, wind farm controllers, PMUs, substation automations, and GIS information, and then they are interconnected with high fast capacity your fibers, and they are connected on the wireless networks and something like that. So, so the information exchange is very fast, and which give us some kind of belief that, yes, we can attain, or we can optimize the things, or we can take a decision in most optimal way, or we can take some decisions in the intelligent way, uh, and we use or maximize the our profits basically. So the agenda is not on smart grid, but yes, smart grid is one part, because I'm trying to connect it. So we want to connect, we want to control this thing in most intelligent way, and this is possible because of the efficient exchange of the data. So in the smart grid is a big structure. Let's take a small part of it. Let's talk about the microgrid, where what we can think of that, okay, this is one region, okay, or it's a kind of one or few buildings in a particular region there, where these buildings, they have their own distributed generation, they have own small wind system. So and there is AC bus, where we can connect all AC generations and all AC loads. There can be a DC bus also, where we can connect DC generations, like from power, solar PV, fuel cell, or storage. We can connect our load, DC load, directly to it, and then we can put AC DC converter in between. So this area, this section is basically one small region, and where they have certain kind of a generation and the load there. And there is a point of common coupling, PCC, which is basically connecting this section with the main grid. So what the idea here is, like, this system is self-sustained system. It tried to meet the load requirements from their own generation, and in case they need more power, they can take it from the main grid, or if they have excess power, they can send it to the main grid. If this PCC switch is on, we call this is grid connected microgrid, and if this PCC is off, then we can say this one is islanded microgrid. So this one is small, you can think of a small sector or small area or a group of buildings there, and this is how they work it. But just think of it like if in your whole city is divided into some small microgrids. So there are so many small regions there where they have their own generation, and then they have their own load. So these are the basically different microgrids. The microgrids, they can be connected with each other. You can see here, like 15 is connected with 16, 15 connected with 24, with 17, with 18, and they are connected with the main grid also. Idea here is like, okay, if there is a requirement at more power at microgrid 19, it can take it from 27, 16, 18, 21, 36, and microgrid 3, or it can directly, or it can take it power through the main grid. So these all the neighboring one, they send it to grid and send it back, but that's not a good idea. If they have their own linking connection, so they can take it from the neighboring microgrids to meet their own requirements. So that will reduce some kind of stress on the main grids and all these things. But this picture gives us an idea that now my system become more and more complex. How I can control that such type of a complex system, because in your microgrid you have many resources. Maybe you have solar and solar storage, EV will be in future, it will be taken as considered as a source and a sink both, and then a wind also. So you have some resources there. So how to use those resources for your own purpose, and then how to from where to take the power, because these microgrids in future, what we are expecting, if they have their own small generation system, they have their own pricing and all those stuffs will be there. So these things are expected in the future, and then you need to control this whole setup here. And that's the one point of that's one point of it's like area of interesting area of research, that how to manage all these things. So there are certain solutions for this one, and the solutions comes from these two ideas. So one is this idea. This is currently what is working, centralized system. You can see only one brain is there. That means all the information of the consumer loads, that is coming to this VPP or this brain. Similarly, generation information from all the generating units through some fiber connections, that also comes here. And now then this body here take a decision that, okay, which generating unit you has to produce how much so that the load requirement can be fulfilled. But just think of that, if any connection is broken, if this is broken here, so there is no information of the load, how much is the load. So if there is no any information, then how this brain here will take a decision that how much to generate. Similarly here, if this connection is broken, so there is no information about there is no information about how much is the generation is there. So there is some kind of some kind of lack of information exchange, and that will disturb all of the system. This one is one of the disadvantages of the centralized kind of approach. The another thought on this one is like this. So you can see in this picture there, instead of one brain, we have many other brains are there. Okay, so obviously main decision will be taken here, but if this link is broken here, okay, if this link is broken here, then what will happen then? Through this path, you can see that this brain, it will communicate here, or it can change, pass the information here also, that okay, this is the load requirement. And say your centralized control system fails, somehow it is not working, okay, some faults are there. So then these small these brains, they are interconnected, they exchange the information with each other, that it will tell this one load management tell, okay, how much is the load and all this stuff. And then generation, they tell that okay, how much the generation they have, and then they can take their own decision that okay, how much generation is required to meet the load requirement. This is a bit decentralized approach, and can be used in many applications. One of the application you can see on your screen, but we can later we can discuss that what are the other applications where we can implement such type of approaches. So this idea can be realized in one form of thing, and that is basically we treat this brain as an agent basically. So this one, each brain is an agent, and the example can be many, but yeah, one of the example can be considered as a like how your institution works basically. So or how this FTP is organized or some any other application. So let's talk about okay how the working of any institution. So we have in any institution we have certain kind of a uh, uh, so certain kind of a uh, layering, like okay we have director, then we have deans, and then we have HODs, and then we have faculties, and then we have students. Each one is assigned with certain kind of a job basically, and that is basically what we expect here. Or since like this FTP is being organized, uh, so say there are there are three coordinators. So the job of one coordinator is the finance matters. The second uh, job of second coordinator is to connect to the audiences and the experts, and the third one is to take care of the IT platforms to be used here. So they have their own roles, and then I'll try to connect this whole multi-agent with, let's say, successful conduction of this workshop, so that we can easily understand this stuff there. So what is how the agent is defined basically, and what are the various definitions people have used. So 1993, some formulation is there, and you can see that what are the requirements. It consisting of the mental components such as beliefs, capabilities, choices, and commitment. And that is exactly what is basically coordinator of this FDP. He has certain beliefs, certain capabilities, he has choices, like choices of choosing the platform, maybe Cisco, maybe Google Meet, maybe Microsoft, or maybe something else. So choices they have certain commitments. So all these things are if they are there, we can say that is one agent. Later improvement are there, software come into picture, so they talk about okay, when the softwares are there, then they must have some kind of a communication language between them. More improvements are there because now people start talking about intelligent agents. So the definition improves in 1995. That is basically now intelligence means they have perceptions. So now the agent has certain perceptions. It can control the environment, or from the changing environment it can infer certain things. So draw the inferences, solve the problems, interpret the perceptions, determine the actions. These are certain properties which we humans have, and then that the same we expect in the agents also. Then some more improvement keep on coming. So as per the improvement in the technology and the application domain, and looking on the processing parts, people keep on adding the things, and then they keep on improving the definitions and likewise. But we can summarize these definitions like this, that an agent is a computing system or a processing system uh, uh, which has some features, and the features are like autonomy, reactiveness, proactiveness, social abilities, and likewise. So this is an agent. So the simplest form to understand is you treat yourself one agent. So whatever the properties as a human has, now we are looking those things in the computing system, and that is we are considering one agent. Okay, so moving further, the architectures can be single agent based system and multi-agent based system. So then how you can like how you can distinguish them? There are certain things there. Multi-agents means not an, it's just one. The easiest way is that like okay, we have numbers, we have many agents, and we have only one agent there. But we need to see the when we are designing any system, we need to see the four important aspects. What is the environment? Okay, they are going to play. Then what are the knowledge, expert, and skills? How we are designing it, and what is the interaction? How we are putting interaction. These are very important in a way that, okay, like we have three coordinators. One is good in IT part, so his expertise in that one. Second one is good in finance matters, so he or she has expertise in that. Third one is he's having a good lot of he's very active in contacting other people. So they have their own knowledge, expertise, skill. We can use those skills for that particular purpose. You can design them depending upon whether you are looking they're looking towards their uh, their working ways or their common languages, or you are looking some kind of combination. So they have their properties, so you can make a combination of heterogeneous or homogeneous properties of these agents. And very obviously we need interaction. Without interaction, then it is not successful to develop the system. So say you put one sensor on certain circuit breaker. Okay, so that sensor is an agent, and the job of that one is the signal is passed to this that agent. So then that will generate one signal, so that circuit breaker is open, and it will receive signal from some other part, some other agent there. So if there is no any interaction, then there will be mal operation, or the system will fail there. So we need certain kind of interaction between them. This is the important aspect of it. Lot of work now currently people are putting in this one, that how to make your agents learn. So let's take it this way, that an agent performs certain action. Okay, there are many ways to develop it. One is you just when you program it, just put certain kind of conditions, and then you ask that, okay, that particular sensor or actuator or computing unit to behave that way only. So that is pre-programmed kind of structure, but that is one short uh, job assignment and not much learning in there. But in many cases we look for learning. So learning is basically, this is how it learned, that an agent take an action. So action moves into the real world. Real world send two things to two things back to the agent. One is the observations, and the second one is the reward. It can be a positive reward and it can be a negative reward. So if it is a positive reward, it strengthen its beliefs and systems, and if it is negative, then then the agent has to correct the things there. So this one is this approach is basically, you'll find very common if you talk about machine learning. Then it is reinforcement learning of its own, or learn to solve the problem. And this is one of the important aspect when you want to make your agents to learn of their own. So this one is how they learn it. And in the coming slides, I'll discuss more on it. How you can make them means like how they can learn of their own and all these things. Right now we're discussing that how to design these what are the components there. Then planning of the coordinating agent. So the coordination agent, you can have both kind of planning, like centralized multi-agent planning, okay, and you can have a distributed multi-agent planning. Centralized means there is only one coordinator, okay, a coordinator to coordinate this whole event. So all the information should be means there are other people who are working, but all the information should be there. He is the only the decision maker. Okay, so all the receipts goes will be with the main with the coordinating agent, and in distributed, the receipts are being shared. So you can understand it this way, that if what are the drawbacks and the means like good points about these two structures. If all the receipts are given to one person, and that person has to take all the decisions. So if the person is not available because of any reason, then the system fail, because that is the only person who is taking the decision. Second, since all the receipts are received by one agent, and the decisions and everything will be done, so that that particular coordinating agent will be overburdened, efficiency will be low, it will take more time because he or she has to, or that agent uh, has to process so many things. So these are the disadvantages of centralized multi-agent planning. Advantages can be think in one way that the all decisions can be done at one place, the conflicts will be less. Whereas in distributed multi-agent, the what is that all these agents, if there are many agents are there, so they have they shared the receipt of each other. So like here, if there are 3 coordinators, so they have receipt of each other. So if say some person, IT person is not available, so then they other 2 agents, they know that okay, we are using this platform, and then they can in the absence of the IT expert, they can even successfully conduct the workshop. So that's a disadvantage. That's the advantage of your distributed multi-agent planning. Another advantage is distribution is basically the job assigned to each agent is very less. Only specific job is assigned, and because of that, the processing will be fast. It will take less time, and most of time it can be parallel, not sequentially, not required. So it is fast, and then the system become more reliable also. The disadvantage is basically then if they have while designing is poor, then they have a area of conflict which may lead to the some failure of the system. So when you are designing it, you need to see that okay, designing the coordination agent, that okay, what type of topology you want to put in. It can be purely centralized, it can be purely distributed, it can be hybrid also, depending upon the requirements you have. So this is what I'm saying. I mean to say that conflict basically. So you can see that each agent is having an area of influence. Okay, domain area, that okay, these are the things which I can do. Okay, and then this one is also having second agent is also having area of influence. So you'll find there is a overlapping. That means there is some area where the both agents they can take a decision. Then you have to put, when you are designing it, you have to put the conditions that okay, how to uh, how to uh, handle such type of situation when there is a conflict between the multi agents there. So that's very important when you are designing it, designing your systems there. This one is another property, which is another term which is commonly used in multi-agent, that is coherency. So coherency is basically how well the system behave as a unit. So how successfully they organize this workshop, and who are the evaluators? They are the external people. So like for this workshop, the speakers and the participants, they are the people who will make a judgment on the coordination or the successful of this workshop. So that is we are looking for coherency. There must be some kind of a coherency between them, so that the conflicts can be avoided. So this one is another term which is being commonly used when you are looking for multi-agent systems there. When we talk about the applications, there are numerous applications. Let's see where we can apply. First one is if you are building a system to solve complex problem, which cannot be solved by single one. There you can think of that. Okay, let's go for multi-agents. So one idea is if you have big problem, if you are in position to divide the big problem into small problems, and then you can use your multi-agents to solve each small problem, so that you can solve combinedly the big problem. That is one way to think of like where can we use multi-agent or not. If you are dealing a problem which involves many problem solving methods, and require different types of expertise, knowledge and viewpoints, there you can go for multi-agent. Like say, okay, building energy management. So okay, I need for building energy management problem, I need information about the thermal profiling of the building. I need the information about the uh, material being used there. I need the information about the architecture of the building. I need the information about the weather condition in that particular region. I need about the orientation. Then I need about the electrical components used. Then I need the airflow inside. Then I need the occupancy inside. So there are different kind of the things there, and we need different expertise there. We can use such kind of approaches to solve uh, to solve this type of problem. And if we are looking for a dynamic reorganization, there we can use it such type of uh, uh, approaches. And if your information is distributed, like microgrid I'm talking about, we have so many things. Okay, we have so many resources, we have different types of load, we have different types of consumer, we have different type of pricing schemes, and now the things are distributed, information is also distributed. uh, then we can think, oh, it's a good area to implement your multi-agent system there. So what are the advantages of using this approach? Uh, if you design it, it can be extensible. It's robust and reliable. It's computationally efficient because we understand that each agent has to solve a very small problem. So it will take less time and it can be fast. Maintainability is easy because if you want to maintain, you can remove one agent, correct it and put it back. Uh, if your system is distributed, then the removing one agent will not affect much on the working of the system because the rest of the agents will take care of it. Likewise, there is reusability and the costing is less because whole system you need not to shut down the whole of the system. So you can keep on correcting the things and the system keep on working likewise. So those are the good points, but like we need to see what are the challenges when you're designing it. So the one of the most important challenges is efficient and effective interaction protocol. We can understand this point like this, that okay, there are three coordinators of this faculty program. One is from south, another one is north, and third one is of the eastern part of the country, and they know only their local language. Then it's difficult to communicate. They don't understand each other. So that's important, that we must have a common interaction protocol. So if you are using sensors and networks of different actuators, so they must be on a common communication protocol. Otherwise, what will happen, that whatever the signal sent from one will not be received by the second one, or likewise. The second important part is basically when you are designing it. So how you are formulating your problem, how you are decomposing it, and how you are assigning the task to each. There must be clarity. It should not be like some kind of ambiguity in that one or some kind of fuzziness in that. If there is some kind of fuzziness is there, then there will be a conflict, and if there is a conflict, then that will affect the performance of multi-agent system. Then we need to see the how they behave in a coherence way, and then how the team is formation. Team formation is basically, that is basically, you can think of like your organization. So you have one person at the or department, HOD, and then you have some UG in charge and PG in charge and the professors and likewise. So there is some kind of a structuring there, and everybody knows that who is responsible for what and something like that. So that is efficient planning part, and then the learning algorithms, which is very important, that how they learn. What are the approach, what are the different approaches, or what type of approach you want to consider for learning of your agents there. If I talk about the architecture in a broader way, there are two architectures. One is closed multi-agent system, another one is more open multi-agent system. So closed can be like example is there an organization, or you can say a family. Family is closed because that meets all these properties. They have static design. We know that they are only 4-person, father, mother, son, daughter, so it's a static one. And their components and their functionalities are predefined. What is the job of father and the mother and the brother and sister, and they have common language. Each of them can be developed an expert. They are cooperative, okay, and they always work towards the development of their family. So this one is a closed structure, very close. So uh, and there is a very good coherency between them. That is what we are expected there. There are advantages and disadvantages of this kind of structure. What are the advantages? The load is distributed and their expertise. The model is simple because we know that who is doing what. As we know the components, we know their working and their responsibilities. No any big issues with protocols and language, because it's very rare that all the four members speak different languages. They can communicate, they can have a common language also. They are cooperative and they share the things. So in computer or in programming, we can say they can share the architecture and the software. But the disadvantages are there. The maintenance cost be high because they are strongly coupled with each other. Last, they are less fault tolerant. If there is any pressure or any fault on one of the agent, it will suffer. It will put effect on everyone. And then another one is it's difficult to operate with other systems. One family in as such is good, but if I will say that this family and another family, or this family and something else, it's difficult to operate. So these are the certain disadvantages of closed multi-agent systems. In open multi-agent system, there is no any design as such. Each individual single agent is an expert, okay, and can be used in any way. Agent may be non-cooperative, malicious, non-trustworthy, like electronic marketplace, open marketplace, anybody can come and move out of it. There are advantages and disadvantages of such type of network. So each agent is expert, so you can make a modular. They are flexible because they are not coupled with each other. You can create a evolutionary design from them, because since they are not static design, so you can create any kind of design, easy to maintain, and they are dynamic open societies. The disadvantage is basically, since uh, single agent is they are not coupled. So what happened is their behavior is not predictable, because many of them, out of say 10 agents, 5 are malicious. So then we cannot say that whether the system will be stable or not. So it's difficult to predict. Another issue with such type of environment is their language, protocols, and ontology. So that varies from one point to another, because there is a variation between the languages and the protocols. And then system failure cannot be avoided because we don't know them. So both closed and open, they have advantages and disadvantages of their own. So this one is the interaction I was talking about. They must have a proper interaction between each other. Otherwise, there are issues in receiving and sending the signals and making decisions on that one. So why we interact? So this one is philosophically and things which are there and which should be added when you are designing or planning your whole multi-agent system. So there are three important things. We have certain goals, and uh, goals are important for all the agents. these agents, they may have conflicting the things and all these things. So to avoid all these things, we can put some kind of interacting mechanisms. There are resources which may be limited, and many agents, they are sharing those resources. So again, we need to take care. If the interaction is proper, then the resource sharing will be done, and then use how to use the expertise of each agent. So you have designed agents for certain particular purpose, and then those agents, they are expert of certain tasks, and those tasks must be properly uh, executed. For that, we need interaction again. Once it is done there, then two important things are also there. Basically, we have talked about the system, and we talked about the various conditions there. The two things are agent characterization. So those characterizations can be taken like human characterization, same as in the same fashion. So one is self-interested or agents. Like in humans also, we have some people who are cooperative and some are self-centric. So those things are there in our day-to-day life. We found those things there. We want these two also in our system there when we are developing multi-agency, because of their advantages. We talk about the advantages there. So if my agent is interested or self-centric one, it always look to maximize its own goal. Okay, so we can say the accuracy of the job performed by that agent will be high. If the agent is cooperative, then that agent will look for the maximization of the uh, goal, or maximization of the uh, profit with the other members also, or in a system. So it is basically work for the entire system. So if say I'm putting one agent, again I'm going for the same example for a relay operation. So I want that to be self-centric. I want that, okay, whenever it will get an information to operate the relay, it should operate the relay. It should not follow many interactions or many instructions. Basically, one command or information shared, and based upon that, it will take a decision. So at that point, I can make it self-centric. But if I'm taking one coordinating agent which is taking information from all and then doing some kind of management or planning, then I expect that one has to be a cooperative one, likewise. So this is how you characterize your agents there. Communication, I already told you, there must be a common communication protocol there. Okay, how they acquire intelligence? Okay, you can go through this one, but let's talk in a different manner. How the reinforcement kind of learning and these approaches can be used. Uh, let's take one example. That is a very uh, basic example, happened with everyone, that okay, you learn how to drive your bicycle, okay, on a plain surface. So you can drive very easily your bike or your cycle. Say bicycle is the easiest one on a plain surface, and now you are moving on a surface where there is some slopey is there, and there is some water in it. So the surface is very slopey, and it is not very plain. It is somewhat or tilted and something like that. So what will happen? You start move with the same, because you know only the one way that move, how to move on a plain surface. So what will happen? You will fall down. So that is basically you take on action that okay, you move just like you are moving on plain surface, and then you fell down. So that is action is basically there, and because of that action, environment return two things to you. One is the observation. The observation is basically you think you will see that why you fell down, and the second one is the negative reward or punishment, that is you either your clothes get dirty or something like that, or wet or something like that. So what you will do the next time, what you will do is when you are moving on that same surface and slopey one and then some water in there, so automatically you tilt your body in such a way that your CG maintain and you can cross it. So that is the self-learning. So that is basically you acquire certain intelligence, you acquire certain learning there, and that kind of approach is reinforcement learning, where you can learn from this environment in a form of punishment and rewards. Such type of things can be adopted here, where your agents can learn depending upon the conditions there, that what are the what are the observations and what are the rewards and the punishment. This one is FIFA model accepted by IEEE. So this one is one agent platform, you can see here at the top, which has 4 segments there. One is agents, then an agent management system, directory, and the message transport system. And this agent platform will talk to another platform through message transport system. Okay, and then so message transport system where all the messages move. So message move from between agents and the management system and the directory, and likewise. This is how you can implement it for a microgrid. So this one is real microgrid, you can see here. So it can be taken like this, that you can put many sensors at different places, sensors and actuators and all those things. A similar model can be put in that on your computer, where these sensors and the actuators, they send the information here, data information, and that data is basically, then that information is used to take certain actions, and then the signals are sent back to the actuators to operate. So here the things are distributed, you can see, and then various topologies can be done, but you can see there are many agents which are present there to perform such type of action. What are the properties of an intelligent agent? Which agent you can call that, whether this agent is intelligent enough one or not. So here we have, you can see various blocks are there. And when we talk about the property of intelligence, then this block is very important. That is decision making module. Okay, because that is one property of intelligent. It has a decision making process, and it make a decision because it has knowledge. So there is a knowledge base. Okay, so what is it? There is external environment and there is a database. From there data is being collected. This data collected data with the knowledge base, some decision is taken. This decision moves to the action block, which goes to the an external environment, and this action block also, based upon the what are the things or observations or reward, it update the knowledge. So this is how this intelligent agent keep on updating the things of its own. This is another very important area to be taken care, because now the whole control and the processing of all of this whole big system totally depends upon the communications basically. So if it is there, communication is there and it is flowing, then that communication must be secured enough. Otherwise, what will happen? Anybody can interrupt in between and can create a false alarms or false things, and then whole of the system failure may fail basically. So what it is being done is, there are various ways of security architectures, but easiest is like, okay, when you're sending any signal, you just encrypt the message, send it through some channel, and send the key with a different channel, so that later that key can be used by the receiving agent, and it decrypt the message and take actions accordingly. So this one is purely computer science domain. You can see that how to encrypt, how to make your system more and more secure. So security is a one big challenge, and under such type of scenarios there, say how sensitive it can be. Like if you are develop multi-agent system, and you are using to control the microgrid, and if the information is basically hampered by uh, hackers and all these things, so they can do the mall operation of your like generators, or create certain other issues which may create a damage to to your uh, loads and some other factors also. So this area should be taken care that when you are sending the information, it must be the secure network. Moving further is basically designing part of it. So like that we call as ontology. So like if I'm designing or designing a multi-agent system for a microgrid, so I must have microgrid ontology. So there are three sections here, like I put it, some concepts, predicates, and action. So these are the things which we normally use. Like okay, we have fuel PV, fuel cell, DC, load, CSS, PCBV switches, and what are the characteristics or what are we observe there, like power level of PV, power level of fuel cell. Uh, uh, in case of batteries, we see voltage level and current level, and likewise. Similarly, predicates means something to predict. So whether connection is grid connected or not, how much is the shading, load shedding is there or not, or something like that. And then actions. Don't know what is this. Someone is trying to control it. Yeah, please, Yashoda C, can you, you have, I don't know who has permitted you. Someone has permitted you to control the flow of the presentation. Hello, anybody there?
Yes, sir.
Yeah, Yashoda C is permitted to control the presentation, so it's difficult for me to move on.
Sorry, sir, I'm seeing.
Okay, sir. Okay.
Panthoi sir is there, na?
Yashoda C. Some participants or from your side, I don't know.
Okay, I'm seeing, sir. Uh,
Okay, I think it's working now.
okay. Okay, sorry for the inconvenience, sir.
Yeah, it's okay. It's okay. Sometime it happens. So we have as agent action where like we can take a decision that switch is on or switch is off or something like that. So this one is ontology, and we need to develop it. What has happened here? Yes. This one is one way where you can realize if you don't have actual system there, what you can have RTDS, real-time digital simulator, where you can simulate the microgrid, and then on your computer you can have multi-agent system, and then you can connect these two by LAN connection, and then this whole processing here will be controlled through your computing system. So that is one kind of way of implementing this kind of thing there. So now I'm taking few of the case studies, and then I'll take certain examples and certain your questions for towards that. So let me move on to the very interesting case, which is easy to understand. Let's assume this is one of the case there. So you can see here, let's take a case of a hospital. So there is this one is a big hospital there where they have hospital building and their houses. This hospital is having a PV at the maybe say rooftop or some PV form is there. Some storage may be also there, and this hospital is also taking power from the grid basically. So this one is conventional power plant. We have distribution transformer from where it is taking power, and you can see there are a lot of circuit breakers here: CB1, CB2, CB3, CB4, CB5, CB6. Okay. And and let's take a very small simple topology that we have put sensors here, one here on the transformer, one on each of the circuit breakers, one on this solar plant, on the hospital, the house, and ICU, X-ray room, and medical store. So everywhere. And okay, let's take the centralized approach that each of these sensors, they are sending the information to this computer here. So we have central layer is kind of working there. So that's the arrangement there. And now let's take a case when there is a fault occurs on the grid side. So fault is occurred here. So as soon as fault occurs here, so the sensor which is at transformer who is sending the data about the voltage and current, it will send the data here, and immediately we can understood it from there that there is a change in the voltage and current, and that is because there is a fault. Okay, so immediately this system send a signal to the agent at circuit breaker 1 that you open it up. So it will open it. So and as soon as it open, this one is isolated, and then this whole setup was this setup hospital, house, and solar power. So they are in the standalone mode basically. They are in the as not standalone mode. They are in the islanded mode of operation. So now what we will do? How the things will occur or perform? This central unit, you can receive a signal from here, receive the information from the sensor at the solar plant that give me the status, how much power you are generating, how much storage you have, power storage. So this agent at solar power, it will send the information that okay, that this is the solar irradiance, this much is the power I am generating. Okay, and at the same time it also receive the information from the agent from the hospital and house that how much is the load. So based upon these two, it will see that okay, the load balancing can be done. Right, generation is sufficient enough to meet these loads. So so it will, what will happen, that the continuous power flow will be there. Then it at the same time it reset the timers basically, that okay, since there is no power from the grid, this is isolated, keep on sending the information fast, say every 5 minutes or so. Then after 5 minutes again solar power sensor tell that okay, this is the status, this much is the solar radiance, this much is the power I'm generating, and hospital and house, they keep on sending the load information. So with the time we have more data here. Okay, more data from the solar side, more data from the load side. So then it will activate the forecasting agent here, and the forecasting agent will forecast that okay, with this scenario, how much power can be taken from the solar after half an hour, 1 hour, 2 hours, or something like that. At the same time, this forecasting agent also forecast that what will be the load profile of the hospital and the house after half an hour, what will be the load requirement after 1 hour, what will be the load requirement, and likewise. And accordingly, the load is being supplied. Say after 1 hour, now it is say the time is say 2 o'clock, solar radiance is less, the power will be less. So less power, and then this central agent will check that how much is the load requirement. So so if it is the gap is very less, now means like the generation is reduced, load is still more, then it again through the forecasting agent, it will see that okay, how long can we meet from this one, and put certain kind of flag that okay, this is the threshold, beyond that I will not allow. So as soon as this it reaches to the threshold, what will happen, that this multi-agent centralized agent send a signal to circuit breaker 2 to open, because this one is not critical, because hospital is more critical. So after a certain time this will open it up, and now the whole power will be supplied to the hospital. Again it keep on observing the generation, it keep on observing the on this load requirement, and based upon keep on making a decision. After say 2 hours or so, it observed that now the power is much less to meet the whole complete requirement of the hospital. then it will, what it will do, it will send a signal to circuit breaker 6 that medical shop is not very important, so it will open it up. So the whole power will be given to ICU and X-ray room, and later it will open circuit breaker 5 also, so that the maximum power can be given to the ICU, because this one is the most critical load. And it keep on doing, and once it will observe that this fault is cleared, this sensor send a signal that the voltage and current are same, then it will send this centralized unit send a signal to circuit breakers. Okay, you can connect because now we have power. So this one is automated control basically, and the things are managed in most appropriate manner. So this is so you can see here there are agents at different places. Those are basically sensors. They are sending the information. So they are what they are sensing it. They are sending it. They are actuators which actuate it when they receive the signal back, and then the rest of the system operation will be done here: forecasting, decision making, and everything there. So this is how you can realize this whole setup there. So you can find this. This one is another. This is what we have used in our work. Instead of taking many agents, we are able to perform by using 2 agents only. That is basically how you can optimize your thing. I have explained you in the most simple way. So this is how we realized it. This one you can see the figure is in the MATLAB platform. You can see DER is there, grid interface inverter is there, load and measurements are there, so critical loads and non-critical loads, isolation transformer, and all these things. So these sensors, this one is real time operation, basically real time simulation, and then the information or data being shared on the another platform. Again, I don't know. So you can see the waveforms there. The system moves smoothly from one operation, that is grid connected, to islanded mode very smoothly. More details if you want, you can check these papers and this more PPT and all this from my website. I'll share that link at the end with everyone. Okay, so this one, these are the some means picture of some results which we have implemented, what happened before 5, what happened after 5, and likewise, or during the operation, and all these things there. Don't know, this one is again. This pointer is creating a problem.
Oh, sir. Is there any problem, sir?
Yeah, and, yeah, now it is corrected. The same request kiya him again. Okay, so this one is another, that was one case study. This one is another case where we can implement it for energy management. So you can see the case here. Okay, that is basically we have 4 diesel generators, we have 2 PV farms, we have 2 wind farms, we have load here, we have battery. We have taken these data from an island in South Pacific Asian region, and we developed we thought of like putting one multi-agent. So how the things and how the agents are designed for this particular problem. Before going that, I can show you the some of the snapshots. This one is one machine, one computer, on which you can see that DGs are there, wind farms are there, PV, load, and fuel cell. This one is in MATLAB on one computer. This one is agent platform created on another computer. So, very one can say common question is like which language is good to create a multi-agent system. You can, there are lot and lot of such type of softwares or languages available which people have used for multi-agent system. One of the most popular is basically JADE, that is Java based uh, multi-agent software which can be used. We found some issues when we used that one with MATLAB. Some interaction issues are there. Somehow, I mean, it's like that sorted it, but certain issues are, I mean, were there that time, but new versions may have less. But after that, we found that okay, can we create the same multi-agent structure in MATLAB itself? So there are tools in MATLAB where state flow tools and all these things. So we use state flow tools to develop our multi-agent system. So here you can see this one is state flow tool to create a multi-agent system, and this one is Simulink model. Since both are on the same software MATLAB, so the interaction and the communication is much easier, not very task. If we want to know more about these applications and the software and tool, you can go through our one of the paper on review on softwares and application in the power system. You can check it from the website, it is there. So how it look like, this is how it look like. So you can see there is this one is MATLAB Simulink model of the whole of the real system is on one machine, and the multi-agent is on another machine and laptop, and they are connected through a LAN cable. So this one you can see that they are connected through the LAN cable. So we run this model here, and then the data, we access the data, whatever the data we are receiving here on laptop through the LAN cable, and then multi-agent works here and it control the working procedures. Okay, when you run it, how? So this one is architecture here. So just let's understand this one. So what is the job or what is the problem? Problem is we have disease, we have wind, and we have solar, and we have load and battery. So we want to use these resources to meet our load requirement in such a way that it can be most economical. That is one. And second is carbon free, means less carbon. That means try to use renewables as much as possible. And then we also understand that with renewables we have issues because they are intermittent in nature. So the generation is also intermittent in nature. So to meet the requirement and all these things in the real time is a difficult task. Okay. And when we want to do the things in the real time frame, it's difficult to do it like this, because uh, when you uh, when you are okay, you are using computers and you are getting a data, and then you are going to make a decision. By the time your decision comes out, the real if you are working real time, then the process moves in the time basically, and there is a lag between your action and then action instant and the real time instant. So the good idea is, let's forecast the things in advance and let's make certain plan on it, so that whenever we want to take any action, it has to be done exactly at that particular instant. So we need forecasting. So you can see that because of that, the one layer we have created known as forecasting estimating layer. What was job of this? We are forecasting each and everything. PV1 for agent, it forecast what will be the PV after, say, after 1 hour. Similarly, what is the PV of 2 after 1 hour? Wind after 1 hour, wind 1 and wind 2. It has to be wind 2. Wind 2 after 1 hour, load after 1 hour, battery status after 1 hour. So all these agents, they forecast individually what will be the condition or what will be the generation of the load after 1 hour. Now once we have this one, then we need to make a decision that okay, which unit has to produce how much, which has to be on, which has to be off. And this one is basically we have already done in somewhere in third year of our power system or electrical engineering, that is unit commitment, which unit is committed and how much it to generate. So there is another layer. So unit commitment agent, so this one is an optimization agent. Basically it take the inputs from all, use certain kind of optimization algorithm, and come out a decision that okay, this unit has to be on, and they have to supply this much of power. That is basically the job of this one. And if there is a lag, still the power is means like not met, Then we have DG agents basically. So then then that we can take it from DGs basically. Okay, so DG agent this that okay, this DG has to be on or this has to be off. That can be taken from this one. So this is how this architecture is being developed. When you run this whole setup there, it will be like this. This one is front end you can develop. I mean, various ways to develop it. This one is one of them what we have done. So you can see here all these agents are there. So you can see that PV agent is sending the PV1 is sending the information that is 0 power. You can see the how much power it is sending to the UC agent. Similarly, PV2 is also sending, W1 is sending, W2 is sending, load is also sending, SOC is sending. So all the information comes to UC agent here at 0 hour. And then it takes certain action. It sends information to DG1, DG2, DG3 and battery, which has to be on and which has to be off. Similarly, you can see here, we have taken some snapshots, but it is continuous. You can say 0 hour, 1 hour, 11 hour like this. It keep on coming. So you can have whole information like how much is supplied from which one. You can see here. The value is also displayed. Now this front end is your choice how you want to develop it, but this is how it works. So one of the results to share with you, you can see that this one is without any agents. So you can say all the DG generators are used here. No for no whether no any no any power is taken from renewables as such also, because there's not any proper arrangements there, and they are being used here. In the second scenario, you can see that okay, multi-agents are being implemented, and you can see here only 2 DGs, they are sufficient enough to meet the whole requirement. There's no need to run DG3 and DG4. So various scenarios can be observed and can be seen. One can be that only DGs and multi-agent, then DG along with the renewables multi-agent. Then if they are renewables, then we can put another few conditions there that okay, uh, uh, solar availability, not availability, shading, no shading, wind availability, not availability, and likewise. So we can add profiling there. So many scenarios can be generated there, and we found that the operation with multi-agent is much smoother and much better there. So I think yeah that's all about on this topic from my side, because we are left with another 10 to 15 minutes. So now we go for the questionnaire so that we can have questions and we have more discussions on that one.
Yes, sir. Thank you, sir. Thank you
Acknowledge
for
my
giving us
scholars
such.
to prepare this work. Okay, I'm stopping the presentation, and then you can just 1 second, give me a second.
Okay, sir.
Yeah, so now you can either unmute yourself or you put your question in the chat box. I'll try to answer your queries, whatever you have. Or if maybe you have to put another idea to be implemented, we can have discussion on that.
Okay, thank you, sir, for such an informative session and for a deep idea inside the multi-agent system and self-healing system and its application advantages and AMS microgrid and all. Thank you, sir. Thank you very much. And session is open for the questions, if anybody has.
Yes, please. Anyone want to discuss on any part of this presentation or any another problem? Please unmute or you type here so that we can have discussion on that.
You can type questions also in the chat box or can talk with the sir.
Yeah, I'm sharing a link with you. This is my website link from where you can download this PPT and some more PPTs and softwares and the programs and codes, and some list of papers which are related to this and some other domain also. My coordinates are also given, so if you have any query later on, you are welcome to mail me, and me or my team from my lab will respond you very as quick as possible on that.
Yeah, okay, sir. So anybody have any questions right now, or otherwise, sir has told you can ask the questions on given link. Okay, I think there is no any question. So with your permission, sir, we can wind up this session.
Yes, Dr. Sudhir, if no any question, we can close it.
Okay, sir. Thank you, sir. Thank you very much, sir. Once again, thank you very much.
Yeah, thank you very much for introducing me to
Thank
my
you, sir.
colleagues and scholars. Thank you.
Sir, thanks.
So, hello, dear
Yes, sir.
participants. Our next session will start from 12:40, 12:15, I think, right?
Yes, sir.
So,
12:45, sir.
12:45. Okay, 12:45.
Yes, sir. Next session will be started at 12:45.
You can take the lunch in the meanwhile.
Thank you, sir.
Okay. Thank you, sir.
Hello.
Yes, sir.
Yes,
Good
yes, sir. Good afternoon, sir.
Good
Am I audible,
afternoon.
sir?
Yes, you are audible. So our today's session's expert is already joined. So today's shall we proceed?
Yes, sir.
Okay.
Okay, sir.
Nirala, please introduce.
Okay, sir. Yes, sir. I would like to start the session 5 with the permission of Dr. Arnav Ghosh, sir. Sir, can I start the session, sir?
Yes, sure. I'm just sharing my slide.
Okay, so before starting, I would like to introduce about the sir. It gives me the immense pleasure to introduce you all about our eminent expert, our today technical session 5, Dr. Arnav Ghosh, sir. Dr. Arnav Ghosh, sir, working as assistant professor in Department of Electrical Engineering, NIT Rourkela. He received his BTech degree in Electrical Engineering from West Bengal University of Technology and MTech in Product Connection Drives from West Bengal University of Technology and PhD in Controls and Dynamics of DC-DC switching converters from NIT Durgapur. He has published more than 40 papers in various journals. His running projects are design and development of low-power hybrid wind energy system, development and prototyping of multi-port hybrid power electronic converters with advanced control for household nanogrid. With a young scientist and technologist in 2021 and University Silver Medal for standing second in the master level degree examination in 2012. His research interest includes power electronic design of SMPS, higher order power switching converters, microgrid and smart grids, electric vehicle and vehicle to grid application, etc. With this brief introduction, I would like to hand over the session to Dr. Arnav Ghosh, sir, for further proceeding. Sir, please.
Okay, thank you. Thank you, Shruti, please, for explaining about myself. So I am properly audible from you.
Thank you, sir. Yes, sir. Yes, sir. Thank you. Welcome, sir.
I hope my slide also visible.
Yeah. Yes, sir.
Okay.
Thanks.
Okay. So very good afternoon and always very happy new year all the esteemed participants as well as delegates, and especially thanks to Professor Meenal Kanti Sarkar for giving me opportunity to deliver some of my idea with this session. Okay, so my session is titled as Microgrid and SmartGrid control and converter design. Okay, so before starting the session, so we need to know about, so what is the basic motivations, means why we are picking this type of ideas. Okay, so what is microgrid, what is smart grid? Okay, so right now this is very well known topic, so most of you are aware about this idea. So basically I am going to discuss here. So what is the basic opportunity? Why why power electronics converters are very important for these applications? Okay, what is the basic significance of those converter? Okay, what are the basic idea about that converter and their modeling process, and why the modelings are also important? Okay, and very few simulations results I can also share with all of you, so we can justify our ideas about the basic applications for our different power electronics converter topologies in microgrid as well as smart grid application. Okay, so that's the basic motivations for our study. Okay, so and why is that power electronics converter? So basic thing is that so if we see different applications, okay, so especially power electronics converters, especially switching converters, okay, have a versatile range of applications. Okay, maybe some point microwatt to as well as some megawatt range. Okay, so as well as why that microgrid concept has come to our scenario? Right now, all we are talking about different microgrid topologies, different microgrid, smart grid, but that concept of microgrid is not so much new earlier days. We all are aware about it in Ganga Sagar. Okay, so it was in India. So in 1980s, okay, so first microgrid was established over there. So it's run by the DG set. Okay, so microgrid concept is not so much new. Initial days it was there, but day by day or gradually it is getting more popular. Basically, some attributes are there. So all of you aware about different ideas like that, scarcity of the fossil fuels, okay, as well as the problem of the global warmings. Okay, so different global warming as well as other different types of problem means space scarcity. Okay, so if we see initial days when the conventional power plant was there, okay, where we can observe that initially the power plants are established in the nearer to the base load. Okay, what we mean by the base load? Base load means if we think about that when the British government, British was there in India, so that time they are establishing some power plant. Okay, very old power plants also be there. Okay, so we can see, but the localities are there. Okay, so the power plant was situated based on the locality, means as per the requirement of the demand. Now gradually that concept has changed. Okay, now distribution generation and distributed generations concepts are there. Okay, so after that the grid concept has came. So it's not like that only one place person is using that power plant, using the consumptions. Okay, is distributely through in any corner of the our country, so the power can flow from one point to another points. Okay, so there is by through that grid concept as well as bus concept. Okay, so that's the idea. But suddenly, why again we are switching from that very conceptual idea like that. So why we are going for that again like that previous type of concepts? Okay, like this standalone system. Okay, great standalone system for our captive generations. Why? Basically, the thing is that handling the overall system is initially it's grid connected conditions. Okay, and the convention system it was quite complicated. Okay, but what right now the government having different ideas. Okay, different ideas, different concepts they are also implementing to our current scenarios. Based on that, if you see different remote areas in our country, okay, so if where that type of area we cannot provide the, sometimes what happens, the electricities are not there, but it is important. Okay, so now all are digitally connected anywhere. So the how they are getting that type of supply. So definitely captive generations, there's only possibilities, and localized captive generation like standalone system. So we can provide them some, you know that in India there is a huge potential of the solar, but the problem is that solar having some efficiency problem. Okay, that how much your space it is taking, so exact amount of efficiency and other kinds of problem also be there, unavailability of the sources at night time. So it's having the storage having huge potential. Okay, so how the storage, actually storage are there for providing the backup, means providing the reliability of the system. Okay, if the storage is there, so how fast they're transferring the power. Okay, so different concepts are coming and they're integrating each other. Okay, so who will make that integrations, who will taking care about all those things? The sole responsible component is our power electronics converters. Okay, so and who will decide the power transforming or power flowing? Okay, flowing of power from one side to another side, like load side to source side to load side, bidirectional operations, as well as the grid connected conditions when the power will be transformed from the grid side to your standalone concept. So everything is decided by whom? Everything is decided by the controller. Okay, so entire thing is interrelated. Okay, like integrations of the renewables to your system, as well as the power flow management and the power flow directions. Okay, so from why I'm asking about telling about power flow direction, that will come to my next slides. Okay, so when we're categorizing the microgrids, so that's the important thing is their hybrid microgrids. That's why the power flow direction is also important. Okay, so I'm coming to that points. So I'm discussing about very initial portions. Okay, so that's the basic idea, basic concept. Okay, so power electronics converters are playing very important role for making integrations enter the systems. Okay, so if the as well as the controllers also be there. Okay, it's a very vast area of applications. Okay, so here we can see some basic structures of the microgrid. I hope my slide is visible from your end. Okay, so here we can see some basic structure of the microgrids. Okay, so where we can see that here that this one we can say like that it's our conventional power stations, like you can say like that it's our grid. Okay, so here we can see two concepts are always there. So standalone condition, grid connected condition. So another condition also be the grid forming conditions. Okay, so here we are giving more trust on that standalone conditions. Okay, so if the standalone conditions are there, so standalone means for that standalone conditions generations. Okay, generations are as well as important. What are the most important part of the microgrid? Generations. Okay, then storage. Here we can see that generations are there from the diagram, that solar, wind. Okay, and generation means that here we can see also the storage also working as an it maintaining the stability. Okay, it maintaining the overall stability of the system. Okay, suppose because the renewables are intermittent in nature. Okay, so you cannot predict that how much generation you will get from that side. So the fluctuations, intermittency is the basic inherent property of the renewables. So we will maintaining the stability of that bus voltage or grid voltage, that your energy storage. Okay, so energy storage having also different categories. Okay, category like it's an only battery storage system, or it's an hybrid storage system. Okay, hybrid means that battery storage is integrating interconnecting with maybe sometimes ultra capacitors. Okay, otherwise sometimes that that in conventional power system network we are asking about magnetic storage. Okay, we are telling about magnetic storage. Okay, so we are realizing that conventional system with our renewables system through this process. Just for a moment, I am phone call just for a moment. Sorry for that interruption. Okay, so here we can see different renewable sources are there. Okay, as well as we can use the load. Okay, so why we are giving that supply? So definitely load is required. So right now that electric vehicles are very popular in our society. Okay, so electric vehicles, so we can consider as a load, as well as other domestic loads we can also use. If the load concept is there, means load having different types of category, like constant power load, non-linear load, linear load. Okay, so by their nature of their characteristics, so your system need to be improved. Otherwise unnecessary THD will be there, power quality issues will become. Okay, so we have to maintain everything, some IEEE protocols. We are having some protocols, that protocols need to be maintained. Okay, and enter the process, who is controlling over there? So normally you are using the controller. So in single word controller, means single controller, we cannot control enter the process. So normally we are using DCS, distributed control system. Okay, so there are different categories of the controller, like centralized control, decentralized control, and distributed control. Okay, so enter the process will be controlling. Now very recently, last 5-6 years back, not 5-6 years, more than that, 7-8 years back, the concept of IoT. Okay, so IoT concept was came. So everything means it's not like that. Control is only by manually you are doing control. It's not like that. Now, the system is so much smart. So anybody can access this through the cloud. Okay, so you are collecting all the data through the to your local server as well as global server based on your security. Okay, if we are using global server, so there is a not like only global server. So server, if you storing all those data, there is a huge chances for hacking and other problems may be there. Security issues will be there, but it's quite easier concept. Okay, like you are operating your microgrid from remote areas. Okay, so you are in other place and your microgrid is in your remote area. You are controlling through your mobile apps. Okay, like that. The different concept is now coming, versatility of their application. So that's why that microgrid concept is very famous, as well as like that. Now the smart grid concepts are there. Okay, but in end of the day, who will take care about all those things? The power electronics converters and the control systems. Okay, so that's why we are designing the presentation such a manner. So we are discussing about very basic about the power electronics converter as well as their control strategy. Okay, here we can see different structures of the microgrids. Okay, in a topology here we can see which are the important features of our microgrid. So energy demand is required. So how much demand throughout the year or peak time. Okay, so power management. Okay, so energy management in broader area, you can say like that power management system. Okay, so for when you are managing the power, so you need to know about that monitoring of your power, then control and that balance. Okay, control monitoring means how much demand is required and how much availability of your resource is there. Okay, so rest of the portions, if there is additional power in generation, who will take care, means where that power will be dumped. Okay, or if there is a scarcity of the power, who is responsible for providing that amount of power. So you have to monitor the entire the situations, and based on your monitoring concept, you have to control the options. Okay, operations, and for maintaining the closed loop stability or balancing the system. Okay, so here you can see the important features, but the as well as your loads. Okay, as well as your load and the storage system. Okay, it's a radial concept of the microgrid. Okay, so radially connected with your system. Okay, so here we can see some of the very basic idea about our electric grid, then synchronous grid, microgrid, supergrid, and smart grid. So these all are the very easy concepts. So I'm not going to repeat it again. So grid means all of you are aware about it. Here, so India having some national grids. Okay, so that can you can that means PGCIL they are controlling. Okay, so they are controlling the from where to where need to power should flow. Okay, so we are maintaining all those things. Okay, now synchronism is another important issue. If you have multiple resources of the renewables, okay, so there is a problem of the synchronism. Means suppose you know like that you are having different AC sources. Okay, and you are using that AC microgrid. So what happens? So you are having suppose some picohydral means hydel sources are there. Okay, you are having some biomass generator. Okay, on natural gas means that generators are there. So all are in AC. Okay, suppose sometimes you are also connecting your system directly to the utility grid. Okay, so all are in AC. So how if there is some if there is some mismatching of the frequency. Okay, so there is a problem of the synchronism. Okay, that's how do you maintaining that synchronism. So you have to maintain about the performance index of that system. Means what is the ripple factor. Okay, so if all the ripple factors are same, only you can synchronize them. Okay, otherwise some other issues, maybe synchronism problem will be there. Okay, then microgrids that localized grid that I'm telling about you already, you can select that captive generations of that grid. Then smart grid concept also be there, bidirectional power flow with that communication protocols. You are incorporating with your system some communication protocols. Okay, so they are having deciding capability. Okay, so deciding capability means that I'm telling about you everything you are storing in the cloud. Okay, as well as you are accessing the entire the process through the local or global server. So based on your instruction, it will operate. So it having some deciding capability. Okay, these all are the very basic concept about our grid, smart grid, microgrids. Okay, now we are going to be classified. What are the different types of what are the different types of microgrids. Okay, so here based on their applications, okay, and capacity, applications, capacity, rating, we can categorize or we can classify the microgrids in five segments. Okay, here you can see based on the mode of operations. Okay, based on the mode of operation, we can classify it's an isolated microgrid or grid connected microgrid. Okay, isolated means it's in standalone condition, so it is not connected with your national grid. Any other, not like only national grid, you can say like the utility grid. Okay, so the entire process will be decided, means the stability of the standalone grid will be decided, the reliability of your storage. Okay, so your storage should not be failed. Okay, so if your storage has failed, so reliability will not be there. Then grid connected conditions. Okay, grid connected conditions means suppose you are having some generations you are providing to your microgrids. Okay, there are different microgrids is there, and all the microgrids are connected with your grid. Okay, so in that condition, you can say like the grid connected conditions. Then most important features, that is type of microgrids. Okay, what are the different types of microgrids? Okay, so types of microgrids means it's an AC type, DC type, and hybrid. Okay, AC means that coming to my later slide. Okay, so then based on the source. Okay, source it was renewable, diesel, and hybrid. Okay, renewables means like that there is a solar, wind, small hydro, pico hydro, biomass, hybrid. Hybrid means all are there. Okay, diesel there means if you say like the conventional one. Okay, conventional diesel or the conventional means fossil fuel base. Okay, and hybrid means both are there, renewables as well as diesel. Okay, then application based means where you are going to be applied in your microgrid system. So that is based on the scenario. You can select the residential applications. Okay, like in your home. Okay, so that I am telling we are from. We are staying here in the Sundargarh district of Odisha. So Sundargarh district is very remote area. Okay, remote area. It's a border area of Chhattisgarh, Jharkhand, and Odisha. Okay, and it's a very border area, means it's a remote area, it's a hilly area. Okay, so a lot of backward see money, what can I say like that, it's a tribal belt of area, a lot of backward community persons are there. So always government is trying to focus or try to enhance their quality of the lifestyle. Okay, so that's why what they are telling about it. So they are installing different, that rural electrifications. Okay, that's a very well-known scheme of the government, as well as they are also using for some social welfare activities. Okay, so in our institute having some of the responsibility, basically based on the responsibility, government also funding. Okay, so government also funding to our institute to how we can enhance the quality of the life of our local persons. Okay, means those are staying some remote areas. Okay, so like that different robotics applications. Okay, different robotics applications, as well as some that I'm telling about, that captive generation applications. Basically, that our place is high potential for of what we had, not high potential for our wind. Okay, so it's a good potential of solar, as well as good potential of our biomass gasifier and that pico hydro. Okay, these two here you can see some small dam we can see if we roaming in Sundargarh district. This is a very big district in Odisha. Okay, and most of the area is covered by some forest. Okay, so there are different captive generations, means small scale generations of idle. Okay, so government always try to motivate the local person how they are getting their own electricity. So standalone generations is important. That's why telling about the scenario, the residential. Okay, first thing is that first concept is the residential. So in the broader sense, when we are talking about the smart city, government having different schemes, smart city schemes are there. Okay, so they are talking about that building management system. Okay, building energy management, BEMS. Okay, building energy management system in the same concept. Okay, the rural electrification, the same concept they are talking about in different manner. Okay, suppose you are having some own generation, like our institute also having, not like only our institute. If you roaming different railway stations, they are using there are different bridge. Okay, bridge means some companies are there. Okay, like Arju Powers and other names I am not saying. So other they are also making the bridge in between the consumer as well as the government. Okay, what they are doing, they're installing different rooftop solar panels. Okay, rooftop solar panels for what? For their individual generations. Okay, suppose you are using traveling in a railway stations. Okay, you can see there is a smart. You can see some smart their inherent generation is required. Okay, so from where they are getting their inherent generation. So that can there is a two benefits are there. There are two benefits. Number one benefit is that some of the power you can generate from your own side. Okay, so what happens? Your electricity bill goes to be less. That is number one point. Second point is that if you having more space and you are able to generate more power, so you can also you can also government can also purchase that additional amount of power from your organizations. That I am telling about BEMS, Building Energy Management System. That simple concept also coming to our smart city concepts. Okay, so based on the scenario, you can also categorize in the microgrids like residential application, industrial applications, as well as commercial purpose. That I am telling about you right now. That's a commercial purpose. Okay, so from where you are generating your funds, that's a very important issue. And if you have sufficient space of connections for the renewables, sufficient space for generations of your energy from the renewables, so you can take any of the opportunities. Okay, based on the size, you can also categorize in the microgrid in three category: less than 10 kilowatt. Okay, so there are different category. Nano microgrids, before microgrid it is coming nanogrids. Okay, nanogrids is there, microgrids again, the microgrid having less than 10 kilowatt, 10 to 1 megawatt, and more than 1 megawatt. Okay, so based on the applications. Okay, so where you are going to be install the microgrids. Now I am coming very important features of the which one is very important features. Here you can see very important features, the different types of hybrid microgrid, different types of microgrid. Why am I giving more focused on it? Basically, we are discussing about different power electronics converter topologies. That's why it's a very important issue. Okay, so different types of microgrid. So first we can say like that it's a DC microgrid. So DC microgrid, here from the structure you can easily understand. Okay, so here you can see the layout of the DC microgrid, where you can see whatever sources you have, renewables sources, renewables are in grid connected conditions. You can say like that. You can say like that. Sorry, you can say like that for the grid connected conditions. Okay, so whatever energy you are utilizing here, okay, that is DC. Why we are going for the DC microgrid concept, that I am telling, the synchronism problem. If you have multiple resources, we have, okay, if there are options for the frequency mismatching, there is a problem. So that's why what you need to do, you are making all kinds of energy in the DC. Okay, and you are connecting with your system. Here you are using some DC link capacitor that maintaining the bus voltage fixed. Okay, here you can see for that reliability purpose or storage. Okay, energy storage module. So we are using battery, capacitor, and sometimes electric vehicles. So why electric vehicles is connected over here? Basically, if you see that, if you see sometimes electric vehicles also having some storage. Okay, it having battery pack. Okay, so and the energy density of the battery pack is quite high compared to your domestic applications of domestic energy storage energy storage device, energy storing devices like batteries. Okay, so what is the important thing is that basically at the night time, okay, basically when the generations is not there, basically you can see the only PV is there and wind I am just considering. Okay, so PV is not there in night time. Okay, now different research is going on, so how they can also generate. Okay, so from the night time by using moonlight. Okay, so this is in research, up to research level, not for the production level. Okay, so wind is the variations depends. Okay, a lot of intermittency is there. Okay, so at night time means when the load demand is peak, evening time, especially evening time. So you have to give some more energy. Okay, you have to utilize the more energy from the storage. Okay, entire the day the storage can be charged. Okay, can be discharged. Okay, but it can be up to the maximum level of power. Okay, so that battery having, there is a vehicle, so vehicle charger is there. That charger is behaves like a bidirectional charger. Okay, so they are taking the power from the bus to charging the vehicle battery, as well as the vehicular battery if it is totally fully charged. And here you have that amount of peak demand, means demand is more. Then what happens, that additional energy also coming back from the vehicle to your domestic bus. Okay, so and maintaining the grid stability, means domestic grid stability, microgrid stability. Okay, so for this one bidirectional charging station is required. Okay, so that's why vehicle is also be considered in the storage module. And there is an ultra capacitor for you. If you see the transient response, the dynamic response of the energy storage. So when it is discharging, okay. So when it is discharging, it is taking some time to reach to the steady state value, means reference value. Okay, whatever power is required. Okay, so it is taking some time. Okay, basically dynamics of the battery is not so much good, but that initial condition, who will take care about that dynamics? Basically you have to maintain the stability and initial transient condition. If you demand is more and if you don't have such type of capacity, so system will collapse. So who will taking care about this crisis period? Your ultra capacitor or super capacitor, you can say like that, it can take care about this period. Okay, to maintaining the grid stability. Okay, so here you can see different loads are also be there. Okay, so it may be DC load as well as AC load. Okay, AC load as well as DC load. So for DC load you are using DC-DC converter. Okay, and AC load you are using DC-AC converter. Okay, so you can see a lot of converters are there, DC-DC, AC-DC. Okay, for PV, what happened? You know that for solar photovoltaic, that I'm telling about that, telling about that efficiency. Okay, that efficiency is not so much good up to the conventional, compared to the conventional power plant. Okay, so what happened, that you have to extract maximum power point of the panel. Okay, so you have to extract the maximum power from your solar panel. So how to extract the maximum power? Okay, basically the generations from the solar panel is a DC, and here you can see the grid is, means your domestic grid or standalone grid, that is also DC. So there is a, you are required some DC-DC converter that can maintaining, and the gate pulse of the DC-DC converter is controlled by the MPPT algorithm for extracting the maximum power. The main thing is that this converter, DC-DC converter, okay, the main feature is that it is not like that to maintain the stability of that voltage, means maintain the constant voltage of the terminal. The main features of this converter is to extract the maximum power. Okay, so the concept will be like that power. So power may be constant. Okay, so in that case, voltage and current may be varied. Okay, that I am telling like that. Okay, so here you can see for the wind generation, again, then you can also use some MPPT algorithm. For wind generation also we are extracting the maximum power. Okay, so MPPT algorithm also be there. Okay, so based on that, here you can see some rectifier circuit you are using. It's a control rectifier. Okay, so there is a different multi-stage converters also be there. Okay, so other cases, for here you can see the storage module. So storage module, what is there? Different DC-DC converters are there. What is the nature of this DC-DC converter? They're bidirectional DC-DC converter. So I'm coming to some other slides. So where we are discussing about what are the different types of power electronics converters we are using for this system, for the integrated system. Okay, so I hope you can understand. So what is DC microgrid? Okay, then we are talking about the AC microgrid. So whatever you know that there is a controversy. Okay, so there is a controversy in between AC microgrid and DC microgrid. Which one is better? Okay, both are having different advantage. Okay, both are having different advantage to satisfy their performances. So we are also discussing about the AC microgrid. Why we are also bothered about AC microgrid? Basically, you know that your most of the generation, most of the available sources. Okay, sources are that AC in nature. Okay, so only PV you are using getting the DC. Okay, PV and storage that is bidirectional one, that is different one. But in only PV you are getting that DC. You can see for hydel, picohydel, okay, whatever hydel generation, then wind generations, for biomass gasifier that I'm telling biomass, okay, biomass generation, then natural gas generation is also be there. So most of the generation you can see there is a they are in most of the cases they are in AC. Okay, so what happened if you convert them AC to DC, then you are regulating the DC. So that I'm saying that multi-stage converters are required. Multiple stages of application of converters are required. Okay, so multiple stages of converter means that you can see consider about the power level. That power level is not like that 1 watt. That power level is for your captive generation. What was our power level of our domestic applications? If you go for any new connections for your distribution company, you have to give the power rating. Okay, so how much power rating, maximum consumable power rating you are given to there. So if you having AC in your home, so it is 5 kilowatt. Okay, based on the number of AC. If you have 10 AC in your home, that's different. But normally we are giving that in between 3 kilowatt to 5 kilowatt. And initial days when we don't have any kind of AC, we are giving. I just saw my capacity, means capacity of power in my home. Initially it was 0.8 kilowatt. Okay, so it was very less. Okay, so now the system has changed. So when you are going to design that power converter, so therein power rating is, you can understand, so range is more, that is kilowatt range, 5 kilowatt. So the one that I'm just telling about 10 kilowatt. Okay, if you connect your electric vehicle with your domestic microgrid, so it's an range is again it will be high. Okay, it is coming around 100 kilowatt. Okay, so multiple stage of applications of your power electronics converter as well as the power rating is high. So there is unnecessary power losses. Okay, so if you convert all of them in the DC mode, then you can see, so there is a for conversions for your power from AC to DC, so additional power losses will be there. Okay, as well as if you see their switching frequency. Okay, so at that range you cannot use that MOSFET. Okay, MOSFET having switching frequency up to 500 kilowatt. So you cannot design such type of money. You are not able to using MOSFET for this power range. You have to think about other solid state devices like your IGBT. Okay, for high power application IGCT. Now that SiC and GN devices are coming to the market. SiC is right now very well known. GN is coming gradually coming to the market. Okay, but their application is not so much common right now. But still, if you go for the IGBT, the switching frequency range also not to such to be very high. So it will be range of in the range of 10 kilohertz to 20 kilohertz in between. Okay, so that's why the power losses, additional power losses will be there. So what we need to do, we have to think some convention, money. We have to think some a convenient method. So that's why the AC microgrid also popular for it. Okay, so here you can see that based on that generation, so whatever sources you are converting them. Okay, so if you have PV, so definitely you have to again convert DC to AC to integrating that AC bus. But there is some problem in the synchronism, but it can be handle. Okay, so you know the different controls architectures are now available in our literature, like group control, virtual synchronous machine control, now oscillatory control. Lot of controls are there and a lot of person are working in this domain. Okay, so that synchronism is not the big issue right now, it can be handled. Okay, so and here you can see for energy storage, you are using DC-AC bidirectional converter. Okay, and based on the load, if you have DC load, again need to convert that AC to DC conversion, AC to AC conversion for driving the AC load. Okay, and you can able to maintain the grid stability. Okay, your domestic grid stability. So you have to use some suitable control to maintaining the stability. Okay, and if required, so you can also operate it in grid connected condition. Otherwise, you can also work with some standalone conditions. For only for DC, so if you have DC source, here we are making some comparison. Okay, like AC microgrid and DC microgrid. So all the whatever sources are there, you are converting to DC to feed your DC bus. And here all the sources that is converting to the AC and feed to the AC bus. That's the concept. Now we are going to discuss about that hybrid microgrid. So right now that hybrid microgrid is very popular, and why hybrid microgrid? The first question is like that. So basic motivation is that you can see based on your sources. Okay, so based on your availability of the sources, you can implement that hybrid. That I am telling the same concept. The multi-stage of operation of a power electronics converter means unnecessary power losses. Okay, so you have to use optimum. You have to use optimum number of converters for getting your for optimum number of converters for cost efficiency of your system. Okay, if there is unnecessary loss for unnecessary conversion, so that is not cost efficient. So whatever we are discussing here, everything is product related. Okay, so we have to thinking when we are using it in a real time system, how it will be look like that. It's not like that everything is fictitious. Okay, approximated. Okay, so approximation means like that whatever we are thinking, we are implementing. No, it's not like that. Or is it required for our system? That is our fundamental issue. If it is not required, so leave it. Okay, so unnecessary thing we should not do it. Okay, so that's why we are talking everything based on the product oriented. Okay, if it is feasible to development the product, that's what I'm telling. So optimum, if you go for that optimum utilizations of all those power electronics converters, so you can see that the hybrid concept is why it is quite beneficial. Why it is beneficial? Basically, you know that AC sources, if you have more AC sources, okay, so you can directly connect in your AC microgrid, okay, and whatever your DC sources are there, AC sources as well as AC load, okay, so you are connected it to your AC side, AC microgrid side, and whatever your DC sources and loads are there, DC loads and the storage, okay, and the storage also important. So storage you are using DC bidirectional converter, so that you can connect to your DC grid, okay, and sometimes you can see the storage also connected to our connected to that AC side also, AC grid also. Why that I'm coming? Okay, in between AC and in between AC microgrid and DC microgrid, or AC bus and DC bus in hybrid microgrid, so there is a one converter. Okay, that is called interlinking converter. Here you can see it is an interlinking converter. It's an bidirectional converter. That's a bidirectional power flow in between DC to AC bus. Okay, suppose storage is connected here. You can see that ESS means energy storage system. Storage is connected to your AC as well as you can see in DC. Okay, whatever demands are there. Okay, so suppose demand is more, so who will take care about that bidirectional power flow? So definitely this converter, the power flow will be only done by this converter. Okay, so additional power will come from DC microgrid to AC microgrid. Sometimes AC microgrid to DC microgrid. Why two both the side the storage is there? If any case that AC microgrid or any of the case DC microgrid has failed, okay. So any of them has failed, or that interlinking converter that connected in between two microgrid is failed. So for that condition, it can be work. Okay, that's right. So that's why you can see like that. It is once it is writing like the main converter, another one is backup converter. Okay, the same concept in our transmission substation, where main bus is there as well as auxiliary bus also be there. Okay, so main bus normally working conditions, and auxiliary bus where the maintenance is there in your main bus and shutdown conditions. So backup conditions. So one is backup converter is also required. So here you can see the basic structure, basic architecture of different AC/DC hybrid microgrid. Okay, so both the cases you can see bidirectional converters, so bidirectional power flows are there. Okay, so here you can see DC bus as well as AC bus. So AC bus, you know that that I'm telling the storage is there. Okay, AC bus as well as DC bus you can also use, and bidirectional power converter in between that DC bus to AC bus. Okay, that's the basic concept. And PCC means point of common coupling, and it is there when the utility grid. So it maintaining the frequency level. Okay, so fix up the frequency level. How much frequency is the PLL means how much frequency is there. Based on that, you can connect with your utility grid. Okay. So what are the important functions for the power electronics converter? That's the important point. So from that previous slides, what we can see, we can understand that what are the different applications of the power electronics converter. First application is that it's behaves like an interfacing converter. What are the different categories based on their function? First one is that interfacing converter. So interfacing converter means what? Suppose you have solar panel, suppose uh, you have a wind generator, or you have some biomass gasifier, or you have some hydel generation generator. Okay, so the power electronics converter is such, they are interfacing to integrate your renewables to the microgrids. Okay, that is integrating. So that is known as interfacing converter. Okay, that interfacing converter is integrating your renewables to your microgrid. That is number one. That is integrating converter. Second one is that is called bidirectional converter. So bidirectional converter having two types. Okay, one is DC-DC bidirectional that I am telling for energy storage to the DC microgrid. Another one is called interlinking converter. Third one, that is DC-AC or AC-DC bidirectional converter. That is connected in your hybrid microgrid system for DC bus as in between DC and AC bus. Okay, so these all are the very important applications. Okay, that important power electronics converter applications for us. Okay, so now why they are very important? Basically, you have to control. You have to control of what? You have to control the power flow. Okay, so another important issue is the power management system, power flow management system. Suppose you are having multiple sources, multiple resources with your system. Directly you are connecting to the power electronics converter to the bus. So suppose load is there. Okay, now we are varying the load. Okay, so from where the power will come? Okay, so by the thumb rule you can say like that, total power divided by 3. So equally sharing. But if you want to give some conditions, okay, like that, suppose battery is there, wind is there, solar is there, and you are varying the load in morning period, when a daytime conditions. So if one third power is coming from your storage, so that is not required. Okay, so storage can only work in night conditions, and if excessive load is there, only that condition storage may work. So who will decide all those things? Okay, that decision will be taken by the power flow management algorithm, that is called uh, power management schemes. Okay, power management schemes for the microgrid, and who will take care about all those things? The controller. So you have to write the code in the controller. Okay, so that which whatever controller you are using for it, based on that you have to write the code, and you have to burn that code to your microcontroller or your DSP processor. Based on that gate pulse, after writing that code, the based on their gate pulse, the who will operate, the power electronics converter will operate based on the gate pulse, and they can control the power flow. Okay, so both are related to each other. Okay, so what are the protocols and standard that I am telling? So synchronizations protocol. Okay, and how much frequency variation is there maximum, that protocols, what will be the TSD protocol, what is the TSD level, that maintaining the protocols. Okay, then communication protocols. Suppose you are having charger, okay, vehicle is connected to your domestic microgrid, so there is some communication protocol. Okay, so protocols means how fast it is, charging, is it maintaining the tolerable band of your battery life of your vehicles. Okay, so charging protocols. So whatever protocols are there means standards. In measurement point of view, we can say like the standards. Okay, standards means it's a primary standard, secondary standard. So in single word, we are telling about the standards and the protocols. Okay, so why we are following, most of the cases we are following the IEEE guidelines. So that's why it is given like that, IEEE protocols. So I have mentioned some of the protocols. Okay, so for integrations of your distributed energy resources to your power system, it's normal power system. For protocols for the power quality issues, okay, protocols power quality issues means TSD issue means how much harmonics is there. Okay, so based on that we have to design, we have to maintain some protocol. Okay, what happened, we are designing some system and we cannot use like the system like a product. Okay, if it is not following any of the protocols. Okay, what would be the problem, it is follow, if it is not following any of the protocols, so that may cause unnecessary power quality issues with our conventional system. Okay, that's why we have to, that's why we are maintaining in our different appliance ISO we are maintaining. So we have to maintain the protocols. Okay, so now the most important features, that is flowchart for designing the power electronics converter. So from our very basic, from our very previous discussion, what we can see, okay, from there we can understand that so where the power electronics converters are applicable, what is the necessary of the power electronics converters for our microgrid systems. Okay, and the renewables is connected to our bus. So now important thing is that I'm telling. So which topology is important? So, okay, we are having a lot of power electronics converters available in our market area. Okay, but we need to know what are the most important means why we are using that power electronics converter and which power electronics converter is suitable for these applications, that we need to know. The first thing is that topology selections. Okay, why the topology selections are important, we have to maintain that I'm telling now, maintaining the stability end of the day. Okay, so suppose we are taking some example. Okay, we are having some system. Okay, so it's operating fine. Okay, the system having some you are providing some not you, some problem is coming, some disturbances is there in your input side. Input side means suppose you are using 4 renewables, one renewables is not there. Okay, but whatever rated load you have designed, that rated load is connected to the system. Okay, so how the entire system will be managed? Okay, so who will decide? The controller will decide. But you are connecting the entire system, you are physically connected all the system like a power electronics converter. So what is the problem? So means you have to realize the situations. Okay, you have to realize the situations or process the situations after designing the all the components. Okay, all the components and the designing of the controller. Okay, so whatever converters you are using, that is a physical system, and all the processing unit is there, that is in mathematical point of view. Okay, that is in your DSP processor or whatever microcontroller processor, what is real-time processor you are using with your system. Okay, so how we are realizing the system. So whatever topology you are using, that is in that physical system need to be converted in the mathematical point of view. Okay, that means the modeling is very important. Why modeling is important? So you have to realize the problem. Basically, control scheme, whatever you are implementing, that is in your computer or that is in your processor, means DSP processor, whatever microcontroller processor. The controller is there in these conditions. but you have to realize the situations. Okay, means how the control is working fine or not. Means in software you need to check it first. Okay, so that's why the physical realizations of your power electronics converters in mathematical point of view very important. Okay, that's why different mathematical modeling is used. Okay, so normally we are using state phase average modeling. Okay, SSA. Okay, sometimes we are using that means averaging method. Both are more or less same, small signal modeling. Okay, but what is the process if you go for that more accurate studies? Okay, more accurate studies, then you have to go for some other sophisticated controls like discretized controller, Philip method, controlling method. Okay, so now different if you see the literature, you can see different analytical the bioelectronics converters are in different analytical methods. Okay, different methods are there. Why it is important to realize your converter in better manner. After that, the control scheme that I am telling. So you have to pick the controller based on your application. It's not like that I am picking one controller, whatever in my mind, I am picking that controller. No, it's not like that. So if it is really required for your system or not, so that we need to know first. Okay, so basically renewables having intermittency. So you have to select such controller that can handle that intermittency of your renewables. Okay, and that control scheme finally you have to implement it. Okay, so whatever controllers are there, you have to design it, then you have to burn it, then you can implement for your practical cases. Okay, so this is the basic flowchart for how designing process we are maintaining whatever the designing process is there for maintaining our microgrids. Okay, power electronics converters for design the power electronic converters for microgrid applications. Okay, so here you can see we have to see four important features, that is good line regulations. Okay, means if your input side any problems are there, so your output, okay, grid voltage, whatever, when the where the load is connected, that voltage there is no such fluctuation. If the fluctuation is there, that should be in the tolerable range. Okay, and it should be coming back to its rated value. Okay, so that if problem is in your input side, so you can say like that it's a line regulation if it is maintained. Okay, so what is load regulation? Load regulations. So before that, I am telling that overall system, the power is constant. Okay. Suppose if your system is designed, some power is constant. So voltage fluctuation is there, voltage is dipping means current is increasing like that. So power is maintaining fixed. Okay. Whatever loads are there, load voltage is, you have to keep it fixed. Okay. So in that case, power is maintaining constant means voltage is dipping means current is rising, so power is fixed. Okay, after that, after sometimes voltage is comes back to its steady state value, also the currents also come back to its steady state value, but the transient conditions is very important. That's why I'm telling the good transient response based on your control selections. Okay, controller selections, the transient concept will be decided. And that regulations, okay, good. First one is that line regulations means I told you that any problems in your input side, so there should not be any problem in your output side. Some transient some response will be there, but it will be maintained fixed after some time. For load regulation, mean good load regulation means any disturbances in your load side, so load voltage, there should not be any changes in your load voltage. Okay, so most of the cases it is maintaining fixed. Okay, transient behavior I'm telling. So how fast it can retain its your original condition. But the system is huge, big. You are having storage. You are having different RES. Okay, so different loads. Okay, so how your rise time? Okay, rise time. How much value is there in your good transient behavior that you need to study. Okay, so for your means which one is your give money based on that you have to think about it. Okay, and finally we'll maintaining about the stability. Okay, so if the entire if presence of any of the changes, if your system retain is initial condition, we can say like that in maintaining the stability. So what happened here we can see that here we can see that microgrids sorry, that power electronics power electronics converters are there. Okay, so power electronics converters are all are inherently non-linear in nature. Okay, so what type of non-linearity you can see over there? That's your switch on, switch off, means switching non-linearity in single word. You can say like the switching non-linearities are there. So what we need to do, as we are discussing about the designing of the controller, okay, so most of the cases what we need to do, we have to mathematically represent our converters. Okay, so whatever mathematics we are using, we are making the system in linearized condition. It's not like that we are, you can also design your power electronics converter in non-linear modeling approach also. But normally what we are using, so state phase averaging method we are using for making linearizing our non-linear system to linear system. We are using LTI system, linear time invariant system. Okay, so there are some different steps are there. Okay, based on their based on their uh, mathematical process of representations. Okay, so what we will do, so if you see that interfacing converter, most of the cases interfacing converter, okay, we are using which type of converter? So basically boost type of converter, SEPI converter, CHUK converter. Sometimes we are also using buck converter. Okay, so buck boost, buck for bidirectional one we are using buck boost converter. So sometimes it is working buck mode, sometimes it is also working in boost mode. So buck boost converter we are using. So the mathematical modeling is very important. Okay, so for this presentation we are considering the state phase average method for that mathematical modeling of the converter. So here there is some basic steps. Okay, so for step one, what we will do in SSM means state phase averaging method. Okay, we're approximated. Okay, we're approximated the state variables. First, we need to know what are the state variables. Okay, so how do you find out the state variables? What is the definition of the state variables? Minimal number of variables. Okay, minimal number. Okay, that can define your state. Okay, so by that way, how do you find out that minimal number of variables? So you have to find out what is the number of storage, okay, energy storing device in your converter. Okay, so if you have two energy storing device like capacitor, inductor, so the state variables are two. Okay, for inductor current as well as capacitor voltage. Okay, so we based on that we can consider like that. Based on that we can consider such a manner. Okay, so if you have three energy storing elements, so three states variable will be there. Okay, three state variables will be there. Four energy storing element, four state variables will be there. Okay, so first we need to find out the state variables. Okay, if you are able to get the state variables, then what you need to do, you have to write down the switch on condition equations and switch off condition equations by using KVL and KCL. Okay, so means you know that switching converter that I am telling, switching converter on off conditions. Okay, so definitely it behaves like a switch. Okay, so switch is on. So what will be its equations? Okay, you can write down the state equations by using KVL, or you can also write down the equation by using the KCL. Okay, so switch on condition, switch off conditions. This is your first step. So what is your next step? Next step is that then you have to averaging them. Okay, so you have to average the state variables. Here you can see. Then what type of state variable? Duty weighted state variables. Okay, so when switch is on and when switch is off, so you know that some of the positions are there, it is duty weighted. Duty means that function is duty weighted. Okay, that d value can be changed. Okay, the value can be changed 0 or 1. Okay, when it is on you can select that it is d equal to 1, when it is off d equal to 0, like that. So you are writing here duty weighted, okay, average equations. Okay, duty weighted average equations for individual state variables. Okay, here state equations are there. Okay, and it is output equation. Then what you need to do, then we are making the system in linearized condition. For making the system linearized, what we need to implement, we are perturbating the variables. Whatever variables we have, we are perturbating. So perturbating means that variable is function contains one DC value. That DC value stands for uppercase. Okay, stands for uppercase. Another one is lowercase italic value. Okay, having some capping. Okay, it is called ripple value or AC value. So here you can see your individual variable. It is your state variable x equals to capital X. Okay, it is uppercase italic. Another one is that cap value. It is ripple value, or you can select the AC value. Okay, so individual variables. Okay, small AC perturbation representing cap are introduced in the DC steady state quantity, which is represent uppercase letter. Another one is lowercase italic one. Okay, then we are splitting them and put all of them in that equations. Okay, two equations are there. We have put all of them in the equation. Then what we need to do? We are getting one identity. Okay, we are getting one identity. Now separating the identity. Okay, so we are separating the DC component. Okay, left side DC component equal to right side DC component. That is number one identity. Another thing is left side AC component equal to right side AC component. We are separating them. Okay, so from the DC component we can get the steady state value. Okay, and the converter topology, based on the topology of the converter, you can decide the steady state value. Okay, how is the steady state value? Means how much maximum ripple will be there, percentage of ripple. Okay, like that you can categorize them. Okay, and for that AC component, what you need to do, then you have to do some, you are having some AC component, then you make it Laplace transformations. Okay, so after doing the Laplace transformation, everything will be there in S domain. Then what you need to do, you have to, you will get whatever, then control to output transfer functions for the switching converter. Okay, so here you can see the plant transfer function in the form of control voltage to duty. Okay, in the form of control. Why? Here you can see the basic closed loop block diagram of the switching converter. Okay, so input is one reference. Okay, set point tracking. Normally we are telling like that. So some set point you have given as a reference, and output is your voltage. Okay, here you can see all are in cap. Cap means they are in considering, you are considering in AC. Okay, so ripple component. So V0 is there. So what happened normally, you know that normal voltage mode control, what is the basic concept? You have some reference value. Okay, so that is your reference value. Okay, another one is actual value. Okay, that whatever you are getting, whatever you are getting from the output of your system. Okay, so that value should be scaled. Okay, should be scaled and conditions. Why it is called scale? Okay, so that value should be nearer to your reference value. That in control system one terminology is there, set point tracking. Okay, so that value should be nearer to the set value. Okay, set point value. So that's why I'm telling about the scaled value. So if your reference value is 12 and you are getting that actual value, it is 2. So what you need to do, you have to amplify that value up to 12. Then only you can compare with your reference value. Okay, here you are doing the comparison here. So output value is there, here gain block is there. In this case, it is not mentioned because the gain is 1. Both are same. Okay, V reference, V0 reference and V0 are both are in same. Okay, almost same. So now there is a error block is there. Okay, whatever the errors you are getting, so the controller is there to compensate that error. Okay, after getting you will get some control signal. Okay, here you will say control signal VC. Okay, so that control signal, what you do in power electronics converter, so it is slowly varying signal. Okay, it is slowly varying signal, but nearer to the zero. Okay, so then you are comparing the signal with some repeating sequence. It may be triangular one, okay, or it may be shortwave one, whatever requirement. Based on the requirement, you can compare both of them. After getting the compare, you will get some PWM signal. That PWM signal is fed to your switching converter. Okay, so here we are using the DC-DC converter, means interfacing converter we are considering. So then get pulse will be varying. Okay, so get pulse we are providing to the DC-DC converter and you will get some output. Okay, so if suppose any disturbance is there, okay, suppose V0 disturbance means, suppose suddenly load demand is more. Load demand is more means current will be more. In electrical engineering point of view, current will be more, you are making power fixed. So current is more means voltage is dipping. Okay, so V0 actually is dipping compared to your V0 reference. Okay, so error will be more, the controller is there. So controller is there. So controller is try to mitigate, try to compensate the error. Okay, so still some value will be there, that VC value. Okay, that is control signal value. Now it is comparing with your PWM. So that VC value is shift. That control signal value is DC shifting. Okay, it is goes up. Okay, so if it is goes up, so for making the stability, okay, for making the stability, for making that output voltage high, so what you need to, output voltage more, what do you need to do? Your converter should be on for more duration. Okay, so if DC value is high, so you have to fix up the switching logic such a manner. Okay, if it is high means converter PWM on time duration should be high. Okay, should be more of compared to off time duration. Okay, then converter will be more turn on for more time, so output voltage will be automatically more, and you can compensate the error. That's why it is called feedback control. Okay, I hope you are able to understand. So here you can see whatever controller is there, it is in digital condition, digital mode. So your converter, so mathematical modeling of the converter is important to converting your physical system to the mathematical point of representation in the mathematically. Okay, so you can design the entire thing in the software platform, then you can implement it. I hope till now all of you can understand. That's the basic motivations for that mathematical modeling. Now we are discussing about that interfacing converters. Okay, different types of converters are there. Okay, so first interfacing converter. So how the mathematical modeling you are doing, so we can understand. So here you can see for CPP panels are there, MPPT algorithm is using, so DC-DC switching converter is using over there. So normally based on your voltage, okay, the VPV, so which type of converter you are going to be used, that will be decided. Okay, so if you want to boost up that voltage, okay, PP voltage it's 12 volt, and if your bus voltage, okay, bus voltage, DC bus voltage means this is load is connected to the bus. Okay, if it is 42 volt, oh sorry, 48 volt, so what you need to do, you have to step up that voltage, battery voltage to 48 volt. Okay, that is first condition. Okay, suppose it is 12 volt. Okay, generation is in 12 volt or 24 volt, and your load demand is what? Your load demand is only 6 volt or less than 6 volts. So what you need to do, stepping down that voltage. So, so you can use like a step up condition as well as step down condition. So you can use here DC-DC step up converter or boost converter, or DC-DC step down converter, or that buck converter based on your load. So also you can use DC-DC buck boost converter also. Okay, so based on the duty control, okay, whatever it can stepping out that voltage as well as stepping down that voltage. So on generalized converter you are fixing over there. Okay, for controlling your applications. Okay, whatever application you require, so based on that you are selecting the converter. Okay, so so who will control that? Who will control that voltage level? Okay, so MPPT controller you are using. Okay, MPPT controller normally you are using to controlling the voltage level, load voltage level. So means if it is working, means it extracting the maximum power. So whatever we can understand from this slide. So based on the converter topology, based on the application, we have to select the converter topology. It may be buck converter, boost converter, buck boost converter. In practical cases, for in any of the cases, we are using SEPI converter, Chu converter. That is derived from of your buck boost converter. Okay, that's why the converter topology is very important, and the modeling of that converter topology. Okay, here you can see some basic basic structure of your microgrid. Okay, DC microgrid where photovoltaic is connected to DC-DC converter with an MPPT algorithm with your bus. Okay, and electric vehicle is there and storage is there. Both the cases bidirectional converters are there for controlling that grid voltage. Okay, so here we are using fast charging concept. Fast charging normally happened in DC. Okay, DC charging is the fast charging. Okay, for that vehicle. DCC converter. Here you can see this is our MPP region, okay, where we need to fetch the maximum power point. Okay, our target is to point out that MPP value, okay, for extracting the maximum power from the PV panel. Okay, this here we can see different interfacing converters, okay, for for our system. Now, from this previous slide, we can see that we are using buck converter or boost converter or buck boost converter for our interfacing purpose. Okay, so we have to know the mathematical modeling of that converter. Okay, so we are using state phase average method for mathematical modeling of our buck converter, boost converter, or buck boost converter. Okay, so here using mode on operation means switch on condition. So here we can see switch on conditions. What is our it's boost converter? Okay, so it's boost converter. We are considering switch on condition and switch off condition. Okay, we are deriving here the mode on operation in switch on condition, mode to operation in switch off conditions. Okay, all the state equations are there. Okay, after that we are writing the state equations in matrix, both the cases. Now what you need to do, we have to write the generalized equations. Sorry, we have to write the average equations. Okay, based up to on state and off state equation in duty weighted condition. Here we can see it is our output equations for mode on condition, output equations mode to conditions. Okay, so state phase equations are there, state equations are there, and it is duty weighted. Okay, on conditions, off conditions, we are clubbing them. Okay, finally we will find out the state equations. Okay, where you can see it having the function of d means duty. Okay, so when d is 0, it will be turned off condition. When d is on, it will be turned on conditions based on that. Okay, so here you can also see the average equations with duty weighted. Okay, now what you need to do, we have to perturbate that one. Okay. So directly we are not here. We are not directly perturbating. Directly we are using that inverse Laplace. Okay, so inverse Laplace we are directly implemented here. Okay, so for getting that for getting the Planck transfer functions. Okay, so finally we'll get the Planck transfer function for boost converter. From that transfer function, we can observe that one RHP0, right of plane 0, is there in the plant of boost converter. Okay, so due to right of plane 0, so why it is called that's why it is example of a non-minimum phase problem. Okay, non-minimum phase problem means directly it do not affect to the gain, but in case of phase marking, what we can see, there is a phase delay. Okay, suppose it's a second order system. Okay, phase second order system is two poles are there. Two poles may contribute to your system minus 180 degree. Okay, if 1 0 is there in right of plane, okay, so that may also contribute another minus 90 degree. So what we can understand, your gain plot, your phase plot, it reach at the value almost minus 270 degree. Okay, that's why it is called that non-minimum phase system. Okay, so non-minimum phase system, it's maximum phase system. Okay, what we need to do, we have to design such type of controller for these conditions. Okay, it having some inherent phase boosting capability. Okay, so normally we are using lead type of controller. Lead controller having inherent phase boosting capability. Okay, but here you can see the phase delays, phase delay almost 270 degrees. So what you need to do, you can use some lead controller. Okay, lead controller, and with having one pole at origin. Okay, so that can also improve the steady state. That pole can also improve the steady state behavior of your closed loop dynamics. Okay, as that phase leading is there, so it can also enhance the quality of the steady state behavior. Okay, the dynamics performance of your system. Okay, so that's why some special type of controller we can use for this concept. Okay, for buck converter as well as buck boost, boost converter as well as buck boost converter. If we see the modeling of the buck boost converter here, again that state phase average method is using for buck boost converter for mode on condition, mode to conditions. Okay, for mode 1 and mode 2 condition, then we are getting some output voltage equations. Okay, both the mode, and we are averaging the output, we are averaging the state equations and the output voltage equations. Then what we are doing? We are implementing the enter the value. Okay, that you want all the values we are getting, and that plant transfer function that I discussed in earlier slide directly put all those values to that transfer function. Finally, we can get that plant transfer function of buck boost converter. Similarly, we can also get one RHP0 in buck boost converter. Okay, so it also having the problem of non-minimum phase. Okay, so that's why what we are discussing about, we have to implement some special type of controller that is called type controllers. Okay, type controllers to enhance the quality of the converter closed loop dynamics. Okay, the response closed loop dynamics to enhance the quality of the response closed loop dynamics, the converter. So there are three types controller: type 1, type 2, and type 3. Type 1 controller is on only behaves like an integrator. Type 2 is one integral control cascaded with one lead controller. Okay, that integral control with taking care about the steady state response of the controller, when a closed loop response of the converter, and that lead controller is take care about the transient behavior. Okay, these two. Here in type C controller, you can see the structure of the type C controller. We are using one integrator and two lead controller. They are in cascaded in nature. Okay, so similarly, that one integral controller can take care about the steady state behavior. Okay, and that lead controller. Okay, they are cascading each other. They are take care about the transient behavior of our closed loop performance of the converter. Okay. So here we can see some setup, okay, some diagram of the experimental setup that I am telling about, that boost converter, buck boost converter. Okay, both are having non-minimum phase problem. Okay, so that what we need to do, we have to, there is a problem of non-minimum phase problem, so we are using some additional switch over here. Okay, the basic reason for the non-minimum phase problem is to that the inductor characteristics, the energy storing as well as energy is means flowing from input side to load side, means source side to load side, due to direct changing of that one. That's the basic concept of that's the basic reason for the non-minimum phase problem. So additional switch is connected over there in topological manner. Okay, so that can use for dissipating, that can use for freewheeling that additional energy through this path. Okay, that can also enhance the or that can also minimize or mitigate the problem of the non-minimum phase problem in topological manner of the tri-state boost converter. That's the concept of the tri-state. Why it is called tri-state? Normal boost converter having two state. Okay, switch on condition and switch off condition. But in this type of boost converter, some additional state is incorporated where you are using some switches. Okay, switches that is uh, connected parallel across a inductor. Okay, so the freewheeling switches are there. Okay, so additional energy is passing through that path. Okay, that's why it is called freewheeling switch. Okay, and another state is that is freewheeling state. That's why it is known as tri-state boost converter. Okay, so here that converter you can also implement it as for the interphasing converter instead of boost converter. Okay, so tri-state topology of that buck boost also will be possible. Okay, instead of buck boost converter, you can also use such topology. Here some steady state response, okay, of a voltage current, okay, in the inductor voltage, that is your inductor voltage current, and current, okay, inductor current is given. Okay. Then for the multiple sources, if you have two sources, okay, suppose individual boost converter we can also use for individual solar photovoltaic. But what will be the problem? Individual boost converter having only one inductor. Okay, only one inductor, and that is that inductor current is behaving like a input current also. So overall ripple will be more. Okay. So if we go for the interleaving condition, what is the interleaving condition? So it's you just connect two boost converter, okay, but their get pulse of the switches are complementary each other, means one intuitively delay each other. So what happened? So they are connected in interlinking conditions. So they are connected in interleave conditions. Okay. So overall ripple collection, overall ripple cancellation is there in case of input current waveform. For boost converter, here you can see for boost converter only one switches are there and one inductor is there. So boost converter will get only one inductor current, and that inductor current is behaved like a input current. But in case of interleave boost converter, what happened? That two inductor currents, here you can see two inductor currents are there. Okay, they are connecting each other. Okay, and you can see they are in almost out of phase. Okay, so their cancellation, there is a huge chances of ripple cancellation, and finally we will get some lesser ripple of input current. Okay, that's lesser ripple in your input current. So the performance of the dynamic performance of the converter is also good. Okay, that's the basic motivations for switching to the interleave mode of operations. Okay, so if you have multiple renewables, okay, so that interleave converter also known as right now also known as multiport converter. Okay, so multiple sources you are connecting, okay, for multiple converters. Okay, now you are making, it's not exactly parallel operations. Okay, it's not the exactly parallel operation, it is interleaving conditions. Okay, so what I mean, you are cancelling the ripple. So cancelling the ripple means current is will be reduced. So power quality issues also very power quality issues means power quality is enhanced for your system. Okay, so here you can see some dynamic performances with changing of your load. So load is there, load is changing, and you have to see that grid voltage. That means steady state voltage is maintaining. Some transient is there here at that condition due to changing of the load. But input current and base current that are changing. Okay, power is fixed. Okay, so voltage is changing. That's why voltage is changing initially, then it is going to steady state value. Okay. Now what we are getting, so interleave boost also having some non-minimum phase problem. Okay, and tri-state concept is there uh, that can mitigate the issues of the non-minimum phase problem. Okay, so interleave is also good compared to boost converter. Okay, tri-state also very good compared to the boost converter. Now what we are doing, we are cascading them, cascading both the converter, interleaved, tri-state. Okay, so we are cascading that interleave and tri-state and designing some converter. Okay, that is called tri-state interleave boost converter, and that you can incorporate or that you can implement it for the interfacing purpose of your renewables. Okay, so when you can see some diagrams, okay, sorry, some response of the converters. Okay, so for the interleave tri-state boost, okay, some responses are there based on the changing of the load variations. Okay, and the performance you can also see interleave boost, interleave tri-state boost, and tri-state boost. So whatever it is, you will get the moderate response. Okay, middle one. Okay, so both the purpose has to be maintained. Okay, for interleave tri-state boost. Okay, so it having interleave boost also having some advantage, some disadvantage. Tri-state boost also having some advantage as well as a disadvantage. So if you clubbing both of them, so it having some advantages as well as some disadvantages. So you will get some moderate results, but its dynamics or behavior will be good compared to other one. Okay. Now we are discussing about the bidirectional converter. So why it is called bidirectional? So bidirectional concept is coming that uh, bidirectional means both the direction it can flow the power. Okay, both the direction the power can be flow. That's why it is called bidirectional converter. So here you can see, suppose we are taking some example, your system having battery having 12 volt. Okay, and the terminal voltage of the battery is 24 volt. Okay, and your DC grid voltage or bus voltage is 48 volt. Okay, now battery is charging. Okay, so battery is discharging. Okay, so battery discharging means in evening time battery is discharging, so it will be discharging 12 volt to 48 volt. That means the stepping up the voltage is required. So which converter is responsible for stepping up that voltage? So definitely boost converter is there for stepping up the voltage 12 volt to 48 volt. And then morning time battery is charging from the renewables. That means it is stepping down from grid voltage is 48 volt to battery is charging in 24 volt. So 48 volt to 24 volt, so it is stepping down. So charging is there in buck condition, discharging is there in the boost condition. Okay. So here you can see the structure of the battery in boost condition, boost mode operation. Structure of the converter in boost condition. Okay, structure of the converter in buck conditions, and battery is connected over here both the cases, and it is your DC grid voltage. Okay, so if you here you can see both the unidirectional switch. Okay, now what you need to do is you club. Okay, if you replace both the switch in bidirectional switch like that, you are clubbing, you are cascading both the converter like that directly on portion. So what you are replacing the switch, okay, bidirectional switch. Here you can see the diode is there only. Now you are using bidirectional switch. So diode is there, both the cases. Here diode is there, you are using bidirectional switch. So both the operation is possible. Okay, in by using two switch. Sometimes it can be work as a discharging condition. Sometimes it can be work as a charging condition. So that's why both the conditions is possible. Both the way of power flow is possible. That's why it is known as bidirectional converter. So some structure of the bidirectional converters are given here. Some other type of converter also be there, that is called hybrid converter. Hybrid converter means it can your input, whatever input you are having, AC input, DC input, output may be DC as well as AC. Okay, for as per your demand. Okay, if your demand in DC, so you will get DC output. If your demand in AC, so you will get AC output. Okay, so both the condition is possible. Okay, and both the output also be possible. So that is known as hybrid converter. Okay, here you can see some structure of the hybrid converter. Okay, now we are taking some standalone conditions. Okay, some example for the standalone conditions. Okay, solar PV, some standalone condition for solar photovoltaic system where some load is connected and solar photovoltaic system connected to the grid through the DC-DC converter, which is controlled by the MPPT algorithm. Okay, so we are using some bidirectional converter over there. Okay, that can maintain the bidirectional power flow as well as grid voltage stability. Okay, so in this case we are using dual loop control. Okay, dual loop control means outer loop is in your voltage mode control and inner loop is in your current loop control. The time constant. Okay, so time constant in more for your voltage loop control and less in your inner loop control. More than normally, thumb rule is more than 4 to 5 times. Okay, so here we are using the P and O method for the MPPT algorithm. Okay, so you can see some simulation diagram. Okay, so from where the constant output voltage in different conditions. Okay, here we can see the irradiations are changing. Okay, so irradiations are there. Initially it was 800 watt per meter square up to 0.6, then it is changing to nearer to the 1000 meter watt per meter square, and then it is coming to near about 600 meter watt per meter square, as well as temperature level also changing. So without MPPT algorithm, here you can see that green line is there. Without MPPT algorithm, you can see that battery voltage. Okay, panel voltage, whatever voltage, it is not fixing up, so it is varying. Okay, it is voltage is varying, variable in nature, but you are using that voltage controller. That previous slide you can see we are using voltage mode control, so voltage controller is there. Okay, so what we can see that voltage is more or less fixed up around 240 volt. Okay, 240 volt DC. Okay, some curve is there, IV characteristics and PV characteristics curve under different conditions with the changing of the temperature. Okay, so changing of the temperature, you can see how the voltage is changing. Current more or less constant. Here it is, this is IV characteristic and this is PV characteristics. Voltage is there, power, how the changing of that power Okay, current is voltage is more means, sorry, temperature is more means more power you are getting. Okay, then IV characteristics for changing a different irradiations value without changing the temperature. Here we are fixing up the irradiance value. Irradiance value is 1000 watt per meter square. That is fixed up and changing the temperature. In second condition, irradiance are changing the temperature in 25 degrees centigrade. Okay, increasing of temperature means that you know that power level also decreasing as well as the output voltage also decreasing. Increasing of irradiance may cause what happened here. You can see power cut that more irradiance means you know that power is more. Here you can see power is more as well as voltage is more or less uh, that whatever you are getting. Okay, here current also increasing of irradiance means current also you are increasing. Okay, you are getting more current. From the simulation you can see. Now we are using the bidirectional converter, dual loop control that I am telling. So it is your battery and bus. Okay, bidirectional switches are there. Okay, then outer loop is voltage loop control and voltage mode control. Second loop is current mode control. Okay, inner loop. Okay, so bidirectional DCC converter is there. So it's a classic type of chopper. So first two quadrant operation. So positive voltage and positive and negative current. So both the side of current is there means current positive maybe, current negative maybe. Okay, that's why you can understand it's a bidirectional operations. And it's a dual loop control. And when it boost converter one direction, back converter. So charging and discharging based on that. So if it is discharging more voltage, so it is boost converter. Charging is less voltage, so it is back converter operations. Okay, both the mode of operation is there. Then similarly, we are following the process that state SSA method, okay, state phase averaging method. Then finally, we can find out the plant transfer function of the bidirectional converter. With the specifications are given here. Okay, so if this is our linearized transfer function, then we put all those values and we will get the final transfer function. Okay, so we are using some PI controller for only for this study. For inner loop, for voltage control loop, you can see the KPKI value, and for current loop, we are using that KPKI value. So we are using some, initially we are using some ZN method, means you can say like that in singular trial and error basis, trial and error based methodology for stabilize the overall closed loop performance. Okay. So for conditions, you can see battery characteristics. Battery current negative means battery is charging conditions. Okay, so battery is charging, then it is zero, then it is positively discharging condition. So charging condition means state of charge increasing gradually. So in state of charge gradually increasing, then fix it up, then gradually decreasing. Okay, battery characteristics for different mode of operations. So battery voltage. So current is increasing, so definitely voltage is decreasing. Current is increasing, so voltage is decreasing. So fix up the power. Now four conditions are there. Okay, so where PV means power generated by the PV, P load means load power. Okay, two conditions are there. Sorry, two considerations are there. Now four modes of operation or four conditions. What is your mode on operation? Mode on operation means when PPV equal to P load. So your generations, PV generation and load demand both are same. Okay, first condition we are considering without having any storage. Okay, second condition is mode to conditions when PVV generation is more than your load. So with storage, additional power will store in the storage system. Mode 3 condition is PVV is less than payload with storage. So scarcity of the power is there. Okay, so additional required power will come from the storage. And finally, mode 4, PPV is varying. Okay, but it also having storage. Okay, so here we are considering only PPV, means solar photovoltaic power, but you can consider any of the renewables, okay, instead of solar photovoltaic, or you can combine other renewables also with that system. Okay. So first condition, what was that condition? PVV equal to P load without having any storage. So whatever generations are there, initially 6,000 generation, then it is increasing 10,000. what finally it is 12,000. Okay, so definitely load demand also tracking this value. Okay, so exactly matching this one. Okay, power is increasing. Okay, so load current, so voltage is decreasing, means current is also increasing, so voltage is decreasing. So whatever there, PV equal to P load. So this mode, the increase of the load power, load generated PV also increasing. Okay, different conditions are there, and irradiations and ventilation power. Okay, so both the conditions you can check it. So now that back mode of operation. Back mode means batteries charging conditions. Okay, so generation is PPV, MPT algorithm based, it is fixed. Okay. Now load power is increasing. Here you can see load power is increasing. Okay, but PPV is more than your load power. So here you can see load power is 5,000, then it is 7,000, then it is coming 10,000. And here you can see for battery power or PV power, it is nearer to the 12,000. So always more than your load power. So where the additional power will be coming. Okay, so in battery, the additional power is coming. So that additional power, it is 4,000, it is 10,000. So 10,000 minus 4,000, so 6,000. So 6 kilowatt is coming, that battery power. Okay, then gradually changing load power. So it is also gradually changing. Okay, the load power is more here. So definitely battery power will be less compared to the condition one. Then it is goes to nearer to the zero. When load power is comes to the 10 kilowatt. Okay. So additional power is charging to the battery. So battery power is negative means battery voltage is positive, so current is negative. Okay. So here you can see current is negative. Initially current is charging. Okay, charging current, so current direction is negative. Okay, then zero. So SOC is also gradually increasing, then make it fixed. So battery voltage is positive, always current is increasing, and in negative 2 goes to zero. So voltage also decreasing from higher value to lower value. Finally, it is stabilized at 60. And voltage variation with variation the load using the battery. So in load side that is fixed. Okay. Now mode 3 operation. Boost mode operation. Boost mode means battery is discharging. Okay, battery is discharging. When battery is discharging, when load demand is more than your generation. Here you can see load demand starting from 10K. Okay, 10 kilowatt. 10 kilowatt, then 12 kilowatt, then it is 14 kilowatt like that. So PPV is 12 kilowatt. So first, you know that both the cases it is same, 12 kilowatt. Okay, so battery power is zero. Then it is coming 12 kilowatt to 13 kilowatt. So 3 kilowatt problem is there. So automatically that battery is discharging 2 kilowatt. It is 12 and this is 14. Okay, so 2 kilowatt. 2 kilowatt power will be coming from the battery. Initially, you can see the dynamics of the battery. So not directly coming to the steady state power, steady state value. It is taking some time to reach the steady state value. You can see this portion. So okay, this portion. So dynamics is not so much good. Okay, here also the same thing. Additional power will come from the battery. Okay, the load power is increasing the power generated, but PV is not enough to provide it. So the balance power and maintain the DC grid voltage is constant, and constant battery will supply the excess power to the load. Okay, this is for mode 3 condition. For mode 3 condition, that SOC. Okay, so the battery current is gradually increasing from 0 to positive value. So battery voltage is decreasing from 60 to some values are there, standard value which is coming to 59. So battery discharging means SOC also goes down. So here it is 0, no changes of SOC, then goes down. Okay, and load voltage variation. So voltage variations with the variation of the load using the battery is fixed. Load voltage is making fixed. So who will maintaining the stability? Battery. That means storage is maintaining the stability. And who is deciding the gate pulse of that bidirectional converter? That control logic is generating the gate pulse to making that all the system stable in your microgrid. Okay, for mode 4 conditions, both are varying. Solar irradiations and that load. Okay, so initially it was more or less 12 kilowatt power PV generation, then solar radiation suddenly decrease. Okay, suddenly decrease means power generation is half, solar irradiation is change half 50%. So it is coming to 5 kilowatt. PV generation. But you have to make the load fixed, so load power is fixing up to 10 kilowatt. Okay, but from where additional power is coming? Additional power is coming, it is 5 kilowatt near to the 6. So so that 6 kilowatt, so additional 4 kilowatt is coming from your battery pack. Okay, so from the battery pack, we are getting some additional power. So before t equal to 2 seconds. Okay. Load voltage is maintaining fixed. Initially, battery is discharging. Sorry, battery is charging. Here you can see value is less than 0. So battery is charging. In the current is negative. Then battery is discharging. So current is positive. So initially SOC is goes up to high value for charging condition. For discharging condition goes up to less value. Okay. So depth of discharging also important issue. So how much it can be discharged, that also in consideration. Okay. Depth of discharge. The battery characteristics, irradiations are there, and battery voltage initially it is weak, then it is reduced to 59. Okay. Here we can see the SEPIC converter is used like a bidirectional converter. Okay, so it's a power circuit. You can see the power circuit, amplified condition, and overall circuit. Okay, for bidirectional SEPIC converter. Okay, and we can see some of the response from that side. Okay. Now we can most of the power electronics converter portions I have some initial briefing of the power electronics converter, some applications I have given. So we have to discussing about some of the very basic idea about the control design. Okay, so what type of control we are normally using? So we are using here you can see that normally 3 types of control we are using for the microgrid purpose. So one is called decentralized control, another one is centralized control, and distributed control. Okay, so in decentralized control, what happens for individual DGs? DG means distributed generation. We are using individual controller for their controlling the power flow management. Okay, so what happened? There is a no communications between that. We are using local controller. Okay, LC means local controller. Okay, so there is no communication in between that two local controllers. So there is a problem of the stability. Okay, so cognizance problem will be there. Okay, so there is a stability problem, synchronism problem will be there. Okay, that's why what we need to do, we have to we can switch from local control to decentralized controller to centralized control, that is MGCC, microgrid central control. So all the local controllers are communicating through the central control. But the problem, what is the problem in this concept? This concept having more complicated, and that all the data will be coming to central control, they will process. So there is an unnecessary transmission delay, unnecessary delay due to complexity of the controller, and handling also quite difficult. Basically, you have to fetch, you have to monitor all those things, fetching all the data, then you have to process all the data. That's why it's quite complicated sometimes. Okay, and finally we will do what kind of controller we will do, that is distributed control. In distributed control means they are making combination, means coordination between two local controls. Okay, not two, all the local controls individually, as well as there is no central control. So they are coordination control. They coordinate each other. Okay, they are controlling each other, sending the pulse to each other, sending the control signal to each other to make the coordinations. Okay, normally this type of controller we are using. And group control, I know that group control is very much famous right now. DQ control, group control for standalone conditions, for grid connected condition, for maintaining the voltage stability, frequency stability. Okay, so with the variations of the load, this portion is also very vast area. So some of the basic brief I have given here. Okay, so you know that whatever I have told you, so distributed communication based control, communication based control, so interconnections between all the microgrid controllers. Okay, these all for our microgrid control. Okay, so we are having some central of excellence of renewable energy laboratory in our department. So what different projects are actually different funded projects are there for establishing of the lab. Okay, so here you can see some of our generations, means that center of excellence having some of the equipments as well as some generations. So some of them are given here. Okay, so we are having also rooftop generations almost in our department, that is 100 kilowatt. 90 kilowatt is given to the institute level, it's provided from department to the institute level, and 10 kilowatt we are using for our laboratory purpose. Okay, so these all are the discussions of my presentation. Okay, so if you having any query, okay, so I hope you are getting my points. Okay, so if you have any queries, you please ask me so I can rediscuss some of the questions.
Thank you, sir. Thank you for your informative session and giving us the deep idea about the different power electronic converters topology, its modeling, and controller design. Thank you once again, sir. And with your permission, we would like to open the session for the queries. The participants, if you have any queries, please,
Yes,
you
sure.
can talk directly with the sir, or you can write in the chat box also. Hello. Dear participants, if you have any query, please you can ask with the sir, or you can write in the chat box, or otherwise we can wind up the session. I think it's okay. So with your permission, sir, we can wind up the session.
Okay, sure, sir. So thank you all of you for listening my session. Okay, if you have any queries, you can also write me mail personally. Okay, no problem with
Yes,
that. I have already shared my communication details. Okay, thank you.
yes, yes, sir.
Thank you all
Thank you,
of
sir.
you.
Thank you very much, sir. Thank you.
Thank you.
Hello. So this is the time for tea break, and we will start the next session at 3 p.m. Thank you all.
Hello.
Yes, sir.
Good afternoon. Sir, I think
Yeah,
sir
yeah, yeah.
joined, na?
Yeah, sir, it's fine.
Yeah, oh, sir. Good afternoon, sir.
Okay. Okay, I didn't
Start.
Yeah. Good evening, sir.
Good evening. Good evening. ये बंद तो लेनी पड़ेगी क्या बताएगा
Sir, with your permission, can we start the session?
So it will take 2 minutes, sir.
Oh, okay, sir. Okay, sir.
अरे ला यार क्यों दिमाग खराब कर रहा है अगला कर क्या कर रहा है अगला सोच रहा था तो पैरेलल करना तुम हेलो ओ थैंक यू इतने ही साल लेट होगा क्या होगा हेलो
Yes, sir.
Sir, good afternoon,
गुड
sir.
आफ्टरनून
Okay.
आर यू रेडी हेलो
Yes,
Yeah.
sir. We are
Yes.
shall I start
No, sir, just a second, sir. We will just start with your introduction, sir, so that all the participants will hear from
yeah
you.
it's already 1 minute okay
Okay, okay, sir.
okay
Okay.
go ahead there is a lot of stuff I have to roll
Okay,
back
okay.
okay no
Okay, sir.
problem
Okay, sir.
okay
Okay.
please go ahead
Okay, sir. Sir, welcome to the FDP program on recent trends of control system in power electronic converters. It's my pleasure and honor to introduce about Professor Beam Singh, sir. Professor Beam Singh, sir, is Emeritus Professor, Department of Electrical Engineering, IIT Delhi, National Science Chair, non-official independent director of NTPC Limited, Chairman, Board of Governors, Maulana Azad National Institute of Technology, Bhopal, expert member of Governing Council of Central Power Research Institute, Bengaluru, and he has handled more than 75 administrative positions. He has received his Bachelor of Engineering degree from University of Roorkee in 1977 and MTech and PhD from IIT Delhi in 1979 and 1983 respectively. Sir has guided 100 PhD dissertations and 171 ME thesis. He has filed 87 patents. He has published more than 1,000 journal papers and 500 conference papers. Sir has executed more than 80 sponsored consultancy projects. He has co-authored textbook on power quality problems and vegetation techniques published by John Welly. Sir is the recipient of first International Solar Alliance Haryana Kalpana Chawla Award for working towards developing solutions in solar energy sector, INAE Outstanding Teacher Award, IEEE IAS Outstanding Educator Award, Khosla Research Prize, University of Roorkee, J.C. Bose and Bimal K. Bose Award of IETE for his contribution in the field of power electronics, recipient of Eminent Engineer Award from Institution of Engineers, Faculty Research Award as the most outstanding research in the field of engineering, Faculty Lifetime Research Award for overall research contribution at IIT Delhi, and many more awards to list out. Sir has chaired several IEEE conferences and is a member of several professional bodies like Indian National Academy of Engineering, Indian National Science Academy, Indian Academy of Sciences, World Academy of Sciences, Institution of Electrical and Electronics Engineers, and many more. His research interests include solar PV grid interface systems, microgrids, power quality monitoring and vegetation, solar PV water pumping systems, improved power quality AC-DC converters, power electronics, electrical machines, drives, flexible AC transmission systems, and high voltage DC systems. Sir, with this brief introduction, I would like to hand over the session to you for your further proceedings.
Good afternoon to all of you. Thank you, Professor Anil Kumar Holia.
Thank you,
Yeah, so well, I think, can I share?
Yes, sir.
It's visible?
Yes, sir.
Okay. Hide it. How to hide it? There. Okay. No problem. Well, good afternoon to all of you, and thank you very much. I mean, giving me an opportunity to talk to you. I mean, and especially in the faculty development program, or you call it 5-day workshop on recent trends on control system in power electronics converters. Well, I have been asked to talk about on power converters for wind energy conversion system. I'm well, without wasting time, I think we can go directly on lecture. Anyhow, thank you very much. I think Professor Neil already mentioned all these things, so we can go ahead. Little update, of course, are there, just go on updating all the time, also. Well, coming to now energy industry, about the ecosystem. I mean, this energy, you can call it industry, typically consists of two major non-renewable and renewable energy system. Non-renewable is basically two major coal and oil, gas. I hope you can hear. Hello, you can hear? Can you hear? Hello.
Yes, sir. I'm just.
Anil
Yes,
sir,
sir. Yes, sir.
please mute them.
Yeah, I muted them. Yes, sir.
Then the another is renewable energy system. I mean, which majorly consists of course the solar, which came among most of the other later, but it has picked up in probably last 10 years, or typically mainly focusing on 5 years with a very large growth. We will talk about the growth of, I mean, some of them, then wind and the biofuel and hydro and other fuel like. Well, why renewable? I mean, renewables do not deplete because these are natural resources freely available and abundant in nature, and global warming and has hit the public and political conscience and effective method to reduce CO2 emission and clean and pollution free, and it guarantees energy security for countries deploying it. and legislation being passed making renewable energy more attractive. Well, there are key renewable energy sources like solar photovoltaic, solar thermal, and wind onshore and offshore, and hydro. So, we like to talk, of course, the wind, and you can see this is the typical all India capacity. I mean, installed capacity of 373. You can call it like a gigawatt, out of which the renewable is already around 26%. I mean, and this is about how it is the private sector, central, federal government, and state government. I mean, the share in typically, I mean, taken data from the CA website, and these are the typical data that how much is the typically India renewable sector. Out of that, like it's basically 89 gigawatt, and typically the other technology like coming, and of course that is coming to typically we can call it like a wind energy. And well, why wind energy? I mean, like wind is air in motion virtually. I mean, as you can see here. So we can call it the wind energy conversion system, the wind energy conversion of kinetic energy of wind to electrical energy, and proudly serving as a renewable of choice in Europe and the US. And increased size and higher productivity have enabled wind generation to become an increasing competitive alternative to more traditional methods of power generation. And uncertainty is the main problem with the wind production owing to inherent unpredictability of weather conditions. And utilization of wind generation is generally rather low, with most in the 25 to 30% utilization rate. So, well, this is the typically, I mean, the wind power conversion. In a typical system, like you have like a wind turbine with a large blade which are mounted on a hub. Then you have a normally the gearbox. It's not mandatory. It depends on the technology which I mean you are going to take which technology there. So after gearbox you have a generator. Then generator connected through power converters to the typically to the grid to the transformer, and of course with the controller. Sometimes we have a battery energy storage system, I mean, to provide the power leveling so that the intermittency of the wind is not reflected on the grid and of course you have a control uh, with of the whole the system so that's basic concept of the wind. What are the advantage of course the wind power? The wind is power is cost effective, cheaper than the solar. Wind creates the job. It's clean fuel source, it is sustainable, and wind turbines can be built on existing farms or ranches and a small land requirement and compared to solar hydro, and it can be built on onshore and fluctuate less than the solar. The challenges, of course, of wind power is the wind power must still compete with the conventional generation sources on the cost basis, and good land-based wind sites are often located in remote locations far from city where the electricity is needed. The turbine might cause noise and acidic pollution, and wind plants can impact local wildlife. It has intermittency issues, and offshore towers more expensive, and premium onshore sites are sometimes saturated. So, what about the wind power update? I mean, worldwide wind capacity reached 650.7 gigawatt by the end of 2019, and the total installed wind capacity in Asia reached 290.6 gigawatt, 44 of global percent of the global capacity. And in India, wind power installed capacity reached 38.26 gigawatt, and as updated on 31st August 2020. And India had the fourth highest wind installed capacity in the world. India has the second highest wind installed capacity in Asia. So India wind energy sector is led by indigenous wind power industry and has shown consistently progress. While expansion of the wind industry has resulted in a strong ecosystem, the project orientation capability and manufacturing base about of 10 gigawatt per annum, and India currently has the fourth highest wind installed capacity in the world, total installed capacity of 35.6 gigawatt as on 31st, and has generated typically 52.66 billion units during 2017-18. The government is promising wind power project in entire country through private sector investment by providing various fiscal and financial incentives such as accelerated depreciation benefit concessional custom duty exemption on certain component of wind electric generators. And besides, generator-based incentive scheme was available for the wind project commissioned before 31st March 2017. So following steps also have been taken to promote installation of wind capacity in the country. The technical support including the wind resource assessment and the identification of potential site through National Institute of Wind Energy, Chennai, located at Chennai. And in order to facilitate interstate sale of wind power, the interstate transmission charges and losses have been waived off for wind and solar project to be commissioned by March 2022. Issued guideline for tariff-based competitive bidding process for procurement of power from the grid-connected wind power project with an objective to provide framework for procurement of wind power through a transparent process of bidding, including the standardization of that process and defining the roles of responsibility of various stakeholders. And the guideline aim to enable the distribution licensee to proceed to procure wind power at competitive rate in a cost-effective manner. Well, what is the typical potential of wind energy in India? The wind is an intermittent and site-specific resource of energy, and therefore an extensive wind resource assessment is essential for the selection of potential site. The government, through National Institute of Wind Energy, NIWE, has installed over 800 wind monitoring stations all over the country and issued wind potential maps at 50 meters, 80 meters, and 100 meters above the ground. And the research assessment indicate a gross wind power and potential of 302 gigawatt in the country at 100 meters above ground level, and most of this potential exists in 7 windy states. And these are the typically the potential of wind energy in India state-wise. I mean, Gujarat have a highest potential. Typically, you can call it like it's have a around 84 gigawatt, then 18 gigawatt in Rajasthan, then Maharashtra around typically 45 gigawatt, then Tamil Nadu around 34 gigawatt, Madhya Pradesh 10 gigawatt, Karnataka 55.86 gigawatt, Andhra 44 gigawatt, and Kerala have a 1.7 gigawatt approximately. So this is typically the potential. I mean, typically you can call it achieved by NIWE, and the potential of energy other states are also, I mean, are given here. Sorry. And this is typically the Indian annual and cumulative installation growth. So wind power installation was 2 gigawatt in a financial year 1920, and cumulative installation of stood 37.69 gigawatt. Like, of course, the wind came much before and gone very fast, and than the solar. But of course, solar came very slow, and then it surpassed it. Like, so this is typically you can call it in India cumulative wind power installation by state, different state. Where Tamil Nadu have a total share of 25%, followed by Gujarat 20%, Maharashtra 13%, Karnataka 13%, Rajasthan 11%, Andhra 11%, and Madhya Pradesh 7%, with Kerala and Telangana like only 0.3, 0.17%. Like, well, this is typically the wind install capacity trend in India, how it is going. I mean, in last typically 10 years, like, you can clearly see how it's going to be really up and up, like, and this is the wind capacity worldwide. So India is following almost worldwide trend as far as growth is concerned in last 10 years, like, and this is the total installed capacity. You can call it global means worldwide, and that has gone to in 2019 650.758. So you can clearly see the fast growth rate of this wind generation in last, typically especially in last 1 decade, like, I mean, also. And in the year 2019, both offshore and wind and onshore out has been, I mean, been different part of the world like China, US, Germany, and India. India is a fourth, I mean, typically in this renewable energy generation, I mean, like. And these are typically wind turbine generator power ratings of different industries, I mean, which are varying even starting from around 50 kilowatt going to be order of now a probably 8 order of up to 78 megawatt, like, on. Of course, these are little old, but it has gone much higher, and many industry are coming. Kini, Danvasta, Senercon, G, Micron, Multibird, and I mean, like, and many are not mentioned even like SOG Loan. I'll just mention the next slide. And these are the wind product overview in megawatt turbines, starting from 2 megawatt to going to be 6 megawatt by different industries. I mean, name of an industry like a Geopyros, G Energy, Siemens, Vestas, Sari Power, Multibird, and Enercon. Of course, Enercon is manufacturing the silent pole synchronous machine. They have scaled down the technology to, I mean, usually you can understand this is a silent pole synchronous generator without gear. I mean, like, because you can design the silent pole synchronous generator without any gear, or with large number of poles, you can design in a manner that it matches the same speed as wind turbine of 50 to 150 RPM approximately. And that's the reason, I mean, you don't, virtually it is a scale down of the technology, like, because synchronous, even a silent pole synchronous generators are available even in India itself of 265 megawatt for hydro. So you have to scale down, and the converters are already like HVDC converters. With this technology, such technology is available even in typically 3 gigawatt in the world. So you have to, even in India, there are a lot of HVDC projects, so you have to scale down that technology. And if you really talk about, I mean, like another one, the permanent synchronous generator, you can design without, at low speed again with the gear, which G Pyros is really manufacturing, and they are using IGCT converter, 4-quadrant converter, and of course you can see the rotor diameter. Then the G Energy, of course, are having a DFIG, which normally runs around 1500 to 1800 RPM, depends on the grid frequency. And its usage, of course, 3-stage gear to bring around like 1800 RPM as a synchronous speed, but it runs typically like corresponding to plus minus 30% slip over the synchronous speed also. And of course, people are, Siemens is using synchronous generator again with the 3-stage gear, and they are using like a typically fully automated converters like. And then Vestas is using again high voltage DFIG with 3-stage gear, and even RE Power is also using DFIG, and Multibird of course using a PMHC with single stage gear. So you can see approximately 75% industry of course are using a DFIG or that different technology, like you can say other than the DC machine, all machines I mean are here, whether it is a squirrel cage induction machine or W-fed induction generator, which is mount rotor induction machine, or conventional synchronous cell and pole machine like a typical synchronous generator by Enercon, and PMSC. Like, of course, for very low rating, we use the permanent brushless DC generator also. Like, well, this is the typical data from Suzlon. I mean, their model of typically of 2.1 megawatt, and it's given continuous speed of 3.5 meter per second, rated wind speed 11, and cut out speed of 20 milliseconds. Diameter, of course, of 97 meter. Surface area 7,386 meter square. Of course, can be stored India or North America. And of course, generator they are using typically of DFIG. So asynchronous 3-phase induction generator with the slip rings operated with the rotor circuit inverter system called W-fed induction generator. And this is virtually the generator which have come in the last 2 decades, like anything for wind applications, like, and tower height of 90 meter, and of course the puller tower, and of course blade is by Suzlon make of SB47. And you can see that typically the, and these are the data, of course, the what are the different technology are there, I mean, the along with the speed and power. So you can say Siemens is manufacturing PMSG, as well as they are manufacturing a squirrel cage induction generator of different rating up to going to be rated power. You can clearly see it, and then their speed also you can see it. Also, similarly, the Vestas is of course W-fed induction generator, again for the typically going to be different power rating starting typically even a 2 megawatt to going to be like order of 8 megawatt. Then the economic Darwin, they are using PMSC. I mean, like, of course, the benefit of PMSC up to 5 megawatt, and they have a, I mean, without any gear. And Areva PMSC and Sevillon W-fed induction generator of different rating up to 2 megawatt to 6.15 megawatt rating. Like, and then the G, again the DFIG. I mean, GE itself in Bangalore, they, I mean, developed this technology in around year 2000. Like, I mean, also in up to reasonable rating, you can see clearly here that FIG are up to, you know, here it is shown. I mean, like GE manufacturing typically, Assam is manufacturing around 6 megawatt, but other industry are also manufacturing. Even some industry are manufacturing to 8 megawatt. Like, then Barwin again DFIG, and Enercon, of course, they are using a silent pole synchronous generator. I mean, like, but and Gamesa, of course, PMSG. Then the Garuda PMSG, then annex DFIG, NPEC, again dual speed synchronous generator, dual speed induction generator virtually, and then the final Vixen induction generator, then the of course the variable speed, and see again pole changing in the squirrel cage induction generator, and Suzlon of course are having a different technology like squirrel cage as well as D5G, right? And of course power wind is using the TMSC. So you can see the different technology. I mean, like in wind power generation, but of course the DFIG have taken reasonable share, which came only around couple of decades before. Like the machine which was quite popular up to 1980, I mean, like, or so for variable speed drive, but after 1980, I mean, with the inverters, we have a technology like with the squirrel cage induction motor with the converters. So, well, this has come very, you can call it like a only around 20 years, 80 to 2000, people are almost not using the one rotor induction machine. And year 2000 GE launch, and all the 75% industry are using now W5 induction generator, which is wound rotor induction machine with a couple of the converter on the rotor circuit. There is specific benefit, so we'll talk about when we'll come to the configuration of these different wind generation. There are normally two types of turbine. One called horizontal axis wind turbine. You can see on the left side. Another is a vertical axis wind turbine. And you can see typically the photograph. Which are there in Quebec, Canada, installed in 1984. Okay, with a power rating of 3.8 megawatt, and you can see how vertical turbine and horizontal turbine look like. There, and then you have a typically largest onshore wind farm virtually on the land, and say 8 gigawatt capacity, plant capacity by 20 gigawatt, and it's located in China. Then you can call it largest offshore wind farm, in UK, and 1.21 gigawatt, typically 7 megawatt 174 turbine, like it's installed in 2020 by Siemens in UK. Like, so this is something like you can call it like a offshore means in the water, like onshore means on the land, like, okay. Then these are the typically you can call it like a wind farms in India. So in 1986, the first wind power is set up at Ratnagiri in Maharashtra, and typically in Gujarat and Tuticorin in Tamil Nadu. So these are typically you can call it producing more than the state producing major wind plant producing more than 50 megawatt. You can just clearly see it. In Kanyakumari, Tamil Nadu is a 1.5 gigawatt. Then Jaisalmer is again 1 gigawatt. You can see quite large capacity of different wind farms like in so far in 14 wind farm. Like, so this is the largest rating wind farm of 1.5 gigawatt, especially in Tamil Nadu, and with the different make, you can call it like a turbine like Suzlon, NEC, Micron, Vestas, and Enercon. They put their turbine, and this is typically in Jaisalmer of 1 gigawatt, and the different turbines from again Suzlon of different power rating they put into that. Then in Maharashtra 528 megawatt, and Vestas, typically Suzlon and Micron, they put the different turbine into this wind farm. Then in Maharashtra, this have a different, like you can say different parts, around 9 parts of this, like, and then again in Sangli, Maharashtra, 278 megawatt in the different part, different make turbine like here, and then again, so these are the different parts the installation have taken place of these wind farms. Like, this is in Madhya Pradesh, again of 100.5 megawatt wind farm, and the different you can call it like a in Ratlam, so it's a different company, like developer is Orange Renewable. Like, similarly you have a Karnataka in 56.1 megawatt, and you have again turbine from 34 turbine from Vestas, and of course by different industry owners like coming to operate. So you can call it offshore wind power in India. The first 1 gigawatt offshore wind energy project in India, to Manish set a target of 5 gigawatt of offshore wind installation by 2022 and 30 gigawatt by 2030, which have been issued to give a confidence to the project developer in India. and the first offshore wind energy project of 1 gigawatt capacity is planned in the identified zone B of the coast of Gujarat in order to bring the economy of scale and localization of necessary ecosystem for offshore wind power energy sector. And in principle, stage 1 clearance as national offshore wind energy policy from relevant ministry or department for a 1 gigawatt of offshore wind project in zone B for of Gujarat coast area already been obtained. Further in stage 2, clearance required for carrying out the study survey for selected already obtained by NIVE, and NIVE is the process for collecting geophysics and geotechnical data and expression of interest for both. For the first offshore wind project of 1 gigawatt capacity of Gujarat coast has been plotted on 10th April, and 35 international, multinational and India developer participated in the UI and subsequent consultation process with provided their input. So, well, what has really caused the motivation for wind power generation? Firstly, the energy crisis, which is because of shortage of conventional fuel energy and escalating prices. Another reason is environmental issue like greenhouse gas emission, acid rain, and water pollution. So, we classified typically this wind energy conversion system into two major parts. One is isolated wind energy conversion system. Another is the grid interface energy conversion. So coming to typically isolated wind energy conversion system, I mean the main is like introduction, then the configuration of isolated wind energy conversion system. Of course, there are two technology like a fixed speed and variable speed. And in grid control as well as in isolated typically systems. And I can tell you like why variable speed wind generation, we'll discuss some time later. The variable wind speed generation, I mean with the proper technology you can generate. In spite it needs a lot of sophistication in the sense use almost two converter in every installation, and typically we have a lot of power converter and a lot of sophisticated control, but still we go for variable speed wind generation. The reason being simple, that you can generate around 50% more energy from variable speed wind generation. Like, of course, we'll talk about control and maximum power technique in variable speed generation. So classification we already talk about. You can have like a fixed speed. We like to discuss isolated induction asynchronous generator means induction generator and pumping synchronous generator. And variable speed we like to talk about DFIG, W-fed induction generator, pumping synchronous generator, and isolated synchronous generator. So we can talk about off-grid, that is a small turbine of 52 watt to 10 kilowatt for use normally for battery charging and water pumping, and isolated typically this grid is typically turbine of 10 to 200 kilowatt, reduce gas generation cost in remote areas, wind diesel hybrid system, and a high or low penetration. So this is a typical example about wind farm that you have a $1,500 per kilowatt install capacity, and operating and maintenance cost is around 0.01 kilowatt hour dollar, and selling price again your $0.04 to 0.1 per kilowatt, and single turbine and isolated grid, I mean cost typically higher cost, and feasibility study and development engineering represents the higher portion of the cost, and expect one major component replacement of 20 to 25% of initial cost and rotor blades or gear. So this is typically what is the how the cost distribution is there like. And you can see this typically isolated grid wind farm, which is generally expensive due to cost of transporting diesel fuel in remote areas, and wind turbine reduce the consumption of diesel fuel, and reliability and maintenance are important. So typically the 50 kilowatt turbine, I mean typically in West Bengal, and this is in typically 50 kilowatt in Canada. Then the 50 kilowatt electricity for small loads in windy off-grid areas, and battery in standalone system provide the electricity during the calm period. It's used for water pumping as a water reservoir is storage, and can be used in combination with the fossil fuel generator sets and the photovoltaic array in a hybrid system. So this is typically the power for a telecom tower in Arizona in standalone, and power for remote village in Israel, and hybrid energy system for Chile. You can see the, I mean, order of for isolated system around 50 kilowatt. I mean, these wind farms are available in typically in all around the world, like you can say in India. Last slide we have shown, and we have shown this is in Canada, then this is in US, then Brazil, South America, as well as Chile. So, well, if we come to standalone wind energy conversion system, basically classifying fixed speed and variable speed polymer operation, and challenging automation wind energy conversion system that you have to control the voltage and frequency, then harness the optimum power, then have to provide the load balancing and neutral current compensation, load leveling, and power quality sharing. So again, you can have an isolated asynchronous generator, permanent synchronous generator, doubly fed induction generator actually. So the advantage of fixed speed and disadvantage is the main advantage simple and low cost, cheap and low maintenance, and main drawback is low wind energy conversion efficiency, poor power factor, power fluctuations in output, and high mechanical stress on turbine blade. So this is a scheme of isolated asynchronous generator based typically three-phase system that you have a synchronous generator coupled with the gear through the gear to the asynchronous generator, and then you have a excitation capacitor bank for initially building the voltage. Then you have voltage source converter with the battery, and then you might have a variety of the load. So battery takes care of intermittency of the generation as well as intermittency of the load, and but of course the converter is responsible for regulating the voltage and frequency, So this is typically the scheme that you might have a, again the induction generator, then the capacitor bank, and you have a even for single phase load you can have a neutral from the capacitor as well as the fourth leg of the inverter, and then on the DC link you have a battery for which regulates the voltage and frequency And there is another scheme again for from asynchronous generator that you can have a again with the battery from voltage source converter, but you have a transformer. To change the voltage level. Also typically for the voltage source converter And this is typically another example of voltage source converter with a single phase, three single phase voltage source converter. We give a great flexibility in the control and provide the good neutral terminal as well as with the battery. So it's capable of regulating the voltage and frequency Then you have another configuration with your T connection. Typically to connect your with the two leg voltage source converter, third leg is just meter and the battery there on the DC link There is another configuration that where you have again the battery on the DC link for voltage and frequency regulation, but neutral current compensation is taken care by the zigzag connection, but you have all three leg for voltage and frequency regulation of this system. Then you have typically the star delta transformer for isolation with the battery and voltage source converter, where the load can be at the generator with the three-phase wire system. And this is the control that how we control the typically the voltage and frequency of this system by controlling the typically sensing the load current, sensing the voltage. Also. Then you have another scheme with the two leg voltage source converter and then with the zigzag transformer for providing the local neutral. Your machine don't have a neutral, so you have only kind of ripple field, so you can generate neutral, local neutral from zigzag connection. The another way providing the compensation for neutral current, but the voltage source converter is only two leg with the battery on the DC link There are plenty of scheme which really investigated with some of our students that three leg VSC with the battery on the DC link, and you have a zigzag connection for providing the neutral, local neutral, because machine we are not able to access the neutral terminal And these are typically the control for voltage and frequency. So you are regulating the voltage, you are sensing the voltage and providing the the magnitude or amplitude of them to the you can call it voltage controller. You give the quadrature axis component, of the current with the quadrature axis template generation by sensing the voltage. Similarly, for you have typically the power estimation and then the frequency regulation from which you are getting typically the another component and get the current control of this voltage system. The another control again for voltage and frequency. So voltage, you can clearly see the voltage control as well as the frequency control in the for controlling the voltage source converter with the typically with the battery along with the voltage single phase voltage source converter And this is typically another control for controlling the voltage and frequency. You can clearly see the frequency control on the top, and then other side you have voltage control. So we are able to really get the nice voltage and control units by the unbalanced or non-linear load And with the SRF based voltage and frequency control. So you have a frequency control here, you have voltage control here. This is a voltage magnitude you are estimating, the frequency you are estimating, and then you have a typically two component. You have feedback component from from the load current, and then you are deciding the grid current, or you can call it generator current, and with along with the PLL you convert like a DQ to ABC, and then you have current control So These are the again power balance theory for controlling the voltage and frequency. Then the symmetrical component for theory-based voltage and frequency controller. Then these are the typical results, like you can see for fixed speed with the PI control. So you can say voltage are regulated, frequency is also regulated, and generated power is also, you can say all constant. Only your load is changing. The load is changing from zero to full load, then two-phase load, then single phase, then no load. So under all the circumstances, like you can call it like voltage and frequency regulated, whether linear load, non-linear load, or unbalanced load. And these are performance like a typically of with the dynamic load. You have a like a asynchronous motor. You are starting from this system. You have this kind of profile of the performance like. And this is typically the application of balanced linear non-linear load, typically at fixed wind speed like. And this is again at the typically at variable speed voltage and current of the typically of the generator, because it's isolated system. Then you have a non-linear load, no load, then three-phase non-linear load, two-phase, single phase non-linear load, but voltage and frequency are not deviated. The frequency is also regulated as well as voltage is also regulated. And then this is typically the case when you have a non-linear load at fixed speed. So you are generating constant voltage, constant frequency, and then you have a, for some time three-phase load. Then you don't leave typically the unbalancing into it, and but the generator current are balanced and sinusoidal also, and frequency also remains regulated. You can clearly see the frequency as well as the voltage both are regulated. So this is the case when you are using an algorithm to analyze typically the other cases. And yeah, that is about another power balance theory, which are responsible virtually for voltage and typically the voltage control like. And this is again the power balance theory. So that was the, you can call it like the scheme is extended not only the one generator, you can extend it to the two generators, and they are connected, let's say, to a common bus, and they have their own individual prime mover like a wind turbine as well as the capacitor, and with the capacitor on both the machines. So there are typically, you can call it like we can take, of course, the issue with the decoupled control. So diode rectifier with typically the buck converter is responsible for frequency control by absorbing the typically you can call it active power, and the reactive power is provided typically by, you can call it by STATCOM in this scheme, like whether it is one or two or so. And this is again the voltage and frequency control. So we already talked about that. Here is the voltage control AC controller, and here it is the typically the frequency, typically frequency PI controller. So both the controller, frequency is regulated by, of course, by your buck converter with the resistance, and voltage control by the your voltage source converter working as a DSTAT. So another scheme, of course, with the wind turbine PMSC base, where you have a normally single stage gear and you have a associated like a zigzag connection for neutral current compensation, but you have a 3 leg for your normal load compensation along with the battery for absorbing the power, typically the power of frequency variation. Like this is the control how the frequency is regulated on the top, and lower is the how the voltage is regulated, and you are getting typically the load current, and then extracting the fundamental from that, and from typically from voltage and frequency controller, you are getting from voltage control reactive power, and for frequency control, you are getting active power. And then you are converting from that, you are typically after subtracting the load component, you are getting the what the it should fulfill the generator. Requirement. So once you have reference current, you have feedback current, and you have current control to already. And these are the typical some similarity result where the performance of wind energy conversion system with balance and balanced linear load with fixed wind speed like. Also, but load unbalancing it takes care. You can say on generator winding or generator, there is no difference. Like also quite good performance, and this is the case with fixed speed. Like under different operating condition. Now coming to the variable speed, you can call it wind generation. Why we have to go for variable wind speed generation? You will not surprised to know. The 50% energy can be generated by adopting the variable wind speed wind generation, and that is the reason 75% industry are going to be DFIG. So, well, to start with, a small machine of permanent synchronous permanent brushless generator directly can be connected to diode rectifier, and then with the typically with the capacitor on DC link. After that, it's a voltage source converter. Either you can feed to a you can call it the standalone load, or you can have this power you can feed to the grid also. So variable speed when time or operation, what really features it has? The variable speed, it had to give at variable speed constant frequency generator, and converter rating is a fraction of total. And operation below and above the synchronous speed is possible, and active and reactive power can be controlled in decoupled manner, and power factor of hysteresis side can be typically controlled by controlling the rotor current line. So this is the typical characteristic. I mean, at different pitch angle. I mean, usually we operate with the 0 pitch angle of variable wind speed, and you can clearly see that if you operate at one wind speed, you are not getting the maximum power for corresponding other speed. Like, and of course, for the like a typical stage generator, you have a like a 4 mode. I mean, like subsynchronous, super synchronous for motoring, and subsynchronous, super synchronous for motoring. So this is typically a squirrel cage generator with the gear, and you have a 2 voltage source converter with the DC link capacitor, and after that you have a filter, and you can put either to local load or you can put the grid. Typically, like I mean, with variable speed, and you can operate this asynchronous generator at variable speed, like. And this is typically the how it goes to like a your PSR, also how the your PSF block of this to operate at maximum power, how it is go to. And if you are fitting like a induction generator, then you are using film voltage source converter. So that time you can probably have this speed controller, and then the that gives you the torque producing component, and then you have a like a from this the speed controller you are calculating the in vector control of this induction generator IDIQ on depends on speed they are already decided. I mean, typically IQ torque producing component is decided by the speed controller, and then you have a space factor modulation for controlling, because this you are putting current control, output of the current control is the your VDVQ, and from VDVQ you are converting to space factor the 3 VABBC differences, and that given to the gating signal forward long voltage source. And these are typically control scheme for isolated system for wind speed generation system. And this is typically the people tried even a matrix converter because it can change from variable frequency to constant frequency. That is the requirement of this application for wind power generation when wind turbine is operating at the variable speed, like. And this is the typical case of permanent synchronous generator or permanent brushless DC generator, that after diode rectifier you can have a boost converter, and from this you can have directly MPPT from boost converter, and then the through inverter it can be put to the grid. So usually such scheme is not used for very large rating. I mean, like we have a some limitations of the scheme not to go for high rating, but lower rating these are scheme are quite preferred to. And this is typically, I mean, like normally in PMSG we must have a 2 voltage source converter, and here also you can call it like a by sensing the electrical signal voltage and current, you can estimate the speed as well as position, so that not to sense any mechanical parameter on the shaft of it, and you can feed the independent load also by the converter. And typically the control of that, like how you are going to centralize with maximum power tracking of this your permanent synchronous generator with typically the kind of control, like. Then this is the typically you can call it like a again with the PMSG and boost converter, diode rectifier boost converter, putting to the you can really putting the this power to the grid, or you can have like an standalone system, like. So this is you can call it like how it is the typically two PMSG, one with the battery and then the converter, both side converter. Another on the point of common coupling you have a when a hydro turbine also PMM bounded brushless motor generator line. And this is the control scheme for machine and roadside converters, how it is really converted like that. Because if you are using a permanent, then you have to use a 2 converter of full rating. I mean, because entire process, because you are getting variable voltage, variable frequency, which is have to be rectified by voltage source converter. And of course, we have here typically the kind of battery which takes care of the intermittency of the wind as well as intermittency of the your load on this local micro wind generation. This is the interesting characteristic which I was mentioning, that you have maximum power tracking. I mean, like for irrespective of the generator which you are taking, you have a turbine power and you have a generator speed. So you have to operate at different speed. I mean, starting from typically you can call it like a around 10 rpm, 5 to 10 rpm, you are going to like a 55 rpm. That is the turbine speed, or some of the PMSG case, if there is no gear, both speed are same. But you can see if you could have used the fixed speed, you could not have generated any power, even if you have a typically wind speed of 6 meters per second. But if it's a variable speed, you can even go for much lower wind speed also. So this line on which you see in between the different curve, this is the line at which you should typically, I mean, operate the turbine for maximum power tracking, like, and these are typically the, you can call it the performance of this system with the, I mean, standalone system with the varying the nonlinear load on the system, and you are able to get regulated voltage, regulated frequency, I mean, of this system, like with constant power of this. So this is the another case of like a, that was your nonlinear load, this is with the linear load, and this, so you have it. So here it was the parallel operation of permanent synchronous autonomous wind energy conversion, a new configuration of standalone application, and using two PMSG, a common DC bus and common load side converter, and separate machine for control. And these are typically the scheme that you have a two PMSG. I mean, DC link and batteries are common for both the PMSG. You can have any number of machine which takes care of intermittency of wind, intermittency of typically kind of the solar, intermittency of the load, like also. And this is typically the control here of PMSG, of individual PMSG, that you can operate them in vector control and get a maximum power from these, like. So the objective of the machine side converter is to use maximum torque for maximum power tracking with minimum current, and the reference value for the Q axis component of PMSG current are determined from the difference of desired rotary speed and for MPPT and the sense rotary speed. And the reference value typically for the D components of PMSG are set 0 because it has already permanent excitation. You will be operating, I mean, like a below base speed at almost at like a unity power factor. And these are typically the scheme with the two PMSG, and where the load is connected with the battery on DC link and load is connected after the inverter. And you are controlling typically the, you can call it the wind velocity, and then accordingly calculating the entire system, like. So these are the typical control equations for the tip pitch ratio. Is note that you must have this typical value, I mean, like here by which is the rotary current at the rotor radius, and then the wind velocity and the efficiency. And you can find out from this relation your reference speed for given wind speed, because other parameters are constant, and then you can find out the speed error. Then you can find out the torque producing component of the current, and DXS component you can keep 0 because it is a PMS. And then from these IDIs to from rotor flux oriented scheme, you can just calculate the three phase. You can call it reference current generated from this control algorithm. And this is the typical circuit diagram. Again, the two PMSG with the voltage and frequency. Typically, the voltage, you can call it the, you are changing the voltage and you have a reference voltage, and then you have a typically PI control get a converter reference current. You have a sense converter current, and then you give the switching pulses for the load side converter. So reference three phase voltage, you can have an independent given voltage like a root 2 Vt into typically three phase sine wave of RMS voltage, and three phase load voltage errors you can find out, and then you can put a PI control for all three phase current, and you will get the you can call it three phase load side current errors, like. And these are typical simulation result corresponding to the wind speed of 10 meter per second, and you have a linear load of 25. You can call it, which has linear load of 75 kilowatt and 25 kVR, and generator power is 43. The remaining comes from the battery. This is under the case of your linear load, and this is case with the non-linear load. I mean, like, again with the linear load and non-linear load, and this is a, so that was PMSG. Now it is a DFIG, Double-Fed Next Center for standalone case. So DFIG is a unique, interesting, which suits here. There is a novelty in this case. I mean, when it is connected to the grid, the voltage and frequency are regulated by grid itself. So you cannot change. Only you have to have a maximum power tracking of DFIG. So here, when you have to regulate the frequency, you have to regulate the voltage, you have to regulate the typically even a load also. I mean, like, or you have to compensate the load. If I talk about in DFIG, you have three control variables. One is the your slip, I mean, from vector control. Another is typically your the torque. So you have so one can be responsible for, or you can call it torque producing component IQ. One can be responsible for, you can call it from maximum power tracking. Another responsible to regulate the frequency on the stator side. And of course, you have a battery so that it takes the intermittency of the generation as well as intermittency of load on this system. So load, of course, can be not only necessarily three-phase, it can be like a single phase, or it can be a three-phase for wire system as it is on here. Like, and this is another important aspect of it, that this DFIG, I mean, like, can generate. I mean, you can have a DFIG, let's say, maybe 1 megawatt, but your typically it is capable of generating around 1 you can call it like even a wind turbine can be taken around 50% higher rating. The reason being, on stator side, you can generate around, because most of the induction machine are designed 0.8 to 0.85 power factor, and you operate on stator unity power factor, so you can generate certainly around more than 100% power from stator and 30% for maximum speed, because it's a 30% slip you can generate from the rotor side. I mean, so the machine is capable of generating without exceeding the voltage and current of either stator winding or rotor winding. You can generate around 50% power from this system, like also. So that's the reason the machine efficiency, I mean, like, goes even a supersede conventional synchronous machine. Apart from that, the converter rating is only the partial, around 30 to 40% of the rating, which actually the machine is having initially. Like, so these are typically the control of this DFIG, and the control method as a direct torque control method, how it goes to control. And these are the flux equation, then the voltage equation in DQ. And from there, of course, you are able to get a typically the variables on from rotor to stator side for control purposes, like and phasor diagrams, and these are typically the control, like. So you have a terminal voltage regulation and you have frequency regulation. I mean, terminal voltage regulation give a D axis component, and for your frequency regulation give a Q axis component of rotor current, and then you have a virtually the slip angle. I mean, like, from here, because you have a from frequency regulation, as I told you, like, you have a slip as a parameters, like, I mean, for control. So you have a active power control two component, like a slip frequency and your torque producing component from speed controller, which is for maximum power tracking. You get a reference speed, but the voltage control only you have a one control, like. So that's convert from three-way to your DQ, typically IDIQ and theta slip. You are able to get into three-phase rotor reference current in of slip frequency. You have a sense rotor current, and you give a getting signal to rotor side converter, like, and it works well without any problem, like. And these are the, of course, the equations which are shown in the block, that you have a speed. I mean, like, typically the voltage control as it is shown, then the torque control, then the slip frequency control, so all three, and then you are getting slip angle. So that will really give a new idea how you can really control of these, like. Typically, of course, the reference DQ current are transformed into three-phase reference current. So you have a rotor current from slip angle and the IDIQ for the rotor, like. So that you can have a current control for that purpose, like frequency control. And this is typically how you are getting the slip angle, and you can have a typically the vector control, like. And you can have a stator current only the what we can call it only at unity power factor operating the stator, like, and then stator current reference current, like. These are typically, like, you have a operation at subsynchronous speed. I mean, like, and you can see the here the performance even at unbalanced load, and then you have a, like, a at synchronous speed where the your rotor currents are DC. You can clearly see here the rotor currents are DC here. It is running exactly synchronous speed. Then you are running at super synchronous speed at highest speed, where you have a in the rotor currents are of like slip frequency, but motor you can start the motor, but there is no effect on the your stator voltage and stator current of this, like. So instantaneous power come from the typically for doing starting from the your wind turbine, like. And these are, of course, the corresponding to the D5G operation at super synchronous speed, and your rotor control with the slip frequency, like. Then the operation of this at 12 speed with the fixed linear load. So that is about the load. If it is a constant, it goes value also. And these are the, of course, the characteristics corresponding to having a load power constant. How if wind speed changing, how typically you are getting a different power flow. I mean, in the system, like how magnetic current is increasing, and typically how the wind turbine in standalone mode operating with voltage and frequency control with a non-linear load. Like so, of course, this system is built up in the laboratory by our student, and you can see voltage and frequency are regulated and typically generator currents and voltage are sinusoidal and balanced. Like and voltage TAD is hardly around 3.8%. And you can see the TAD of current is only of generator 3.5%. And for different modes. You'll see when the load is removed from one phase, still the system works well without any problem. Voltage and frequency remain regulated, and still you have a fixed generation as the rotor current. You can clearly see it's not changing with the load. Like, and this is the case with the again load addition. That was loaded. These are all experimental results on developer like in the laboratory. I mean, with our student, and even you are feeding a non-linear load. I mean, the converter which are on the grid side, it is capable of filtering, and you get the typically generator current sinusoidal loads over here. And the TAD of voltage in standalone mode is also only 3.8%, like which qualify well the standard like well, this is you are feeding a non-linear load. In spite feeding a non-linear load, you are able to get the TAD of the generator current only less than 3% all of that. Like, and this is typically the non-linear load removal, how the system goes without any much problem. And when the load is addition, the voltage and frequency remain regulated at the point of common coupling, which is feeding to the load. Like, and then the wind speed. Suddenly load addition, dynamic load addition on this system, it work well. I mean, like for dynamic load, like motor load removal and addition, like and change on wind speed also. And we look into FIG, we put the battery on the DC link, then it takes the intermittency of the load as well as intermittency of the wind generation also. Like also, it works very well without any much problem in standalone mode. And this is the typically control from we are getting from MPPT the reference speed, we are getting a estimated speed, and then we are doing like a typically like fuzzy logic controller for getting the torque producing component, and the flux producing components coming basically from the speed only. And then you have a typically from both ID and IQ of the rotor, and you have a slip angle, and from which you are converting the estimating the three-phase reference rotor current, you have feedback rotor current, and you have a typically the switching of the rotor side converter. And this is load side converter for voltage regulation. And you have a just regulating the voltage, which you really give again from fuzzy logic. You are getting torque your reactive power component and the torque producing component coming from the rotor, and you are able to convert again from the your state. You can see three-phase reference current of state, and you are having you can call it state side converter control with the reference current calculator engine. They are typically the laboratory prototype of the system, what it is developed by student. And you can clearly see the generator current is balanced, sinusoidal, where the load is non-linear and state converter is compensating it. And you can see that typically even the generator current TAD is 4.2% when it's feeding the highly non-linear load of TAD of around 26% also in standalone mode. And the voltage TAD remains in spite of feeding a typical highly non-linear load of 32% TAD, it's only have a voltage TAD of 3.8%. Like so it's regulate the voltage and it's regulate the frequency. These are dynamic performance. You can say your voltage, your stator current and rotor current are sinusoidal, where you have a typically the load current non-sinusoidal, but your load side converter takes care of this non-linearity along with the voltage regulation, frequency regulation. It also supplies the harmonics of the load locally, like and you can see when under the wind variation how the rotor current frequency changes. It passes synchronous speed from low, you can say from above synchronous speed to lower speed is going. I mean, accordingly, we can see it's regulated like, and similarly going to be below synchronous speed to above synchronous speed. How the three-phase rotor currents have become the DC at synchronous speed and pass and during wind speed variation while maintaining the maximum power tracking like also. And this is a case when speed variation is there, so you can just clearly see that I mean the rotor currents are varying from via synchronous speed to higher one and then lower one. So you can clearly see by enlarging that okay how the rotor current become DC in between while you are increasing the typically the speed of the wind as well as decreasing the speed of the wind. So it takes care of, typically constant voltage, constant frequency generation in different varying conditions of the wind variation as well as load variation. Now coming to synchronous generator based wind energy conversion system, conventional synchronous generator, of course, this is for standalone system. So we have a conventional synchronous generator and then followed by voltage source, one voltage source converter, then another voltage source converter with the battery on DC link. Of course, even you can integrate the solar also. It is our student have integrated solar also on it, and then you are able to regulate the voltage across this. So intermittency of the wind generation as well as intermittency of the solar is taken care of the battery in this case. For this standalone or isolated generator with the synchronous generator, and these are of course the control algorithm. We are taking like a load. From nonlinear load current, we are getting fundamental component, and from fundamental component, of course, from voltage regulation, we are able to get it typically D-axis and Q-axis component, and from frequency, we are able to get angle, and there we have a reference. You can call it like a reference DQ current, and then the converting into three-phase current, and have a sensing the current, and have a current control for this converters, like for voltage and frequency control there, and you have a like a MPPT here. Okay, maximum power tracking by typically from the synchronous generator side by estimating the power itself from after the converter from this machine, and then you have a typically like a operation, D-axis component for unity power factor operation for typically of this machine, which can be referred to like a, typically the unbalanced current is equal to V0 in that case. These are the experimental result, how it goes, you are having a quite high TAD, about 25%. Like here with the load current, but the TAD of the, you can call it like a, is quite low. And it is a position, of course, which you are really required for the controller. And here position and speed both are estimated from the algorithm from voltage and current signal only, estimated. This is about the result for solar maximum speed. The solar is also put in this system kind of along with the wind generation, and when the wind varies, how your voltage and frequency are regulated, and you can clearly see like here, you are having quite distorted voltage because of nonlinear load, but when you put the compensator on this kind of system, you are able to reduce the typically the TAD from even 20% to of the voltage. Even at nonlinear, you are able to reduce 3.8% by putting this control. That shows the effectiveness of your control like here. And this is the typically how you are really under load, unbalanced load, how you are extracting fundamental component from typically from the load current like. So coming to like a summary of like your isolated wind energy conversion system. So different topology of isolated asynchronous generator for fixed speed prime mover has been presented, and different control strategy of wind energy conversion system on fixed speed isolated synchronous and permanent have been presented, which are as follows. The type of wind energy conversion: fixed speed with asynchronous generator, and fixed speed with parallel asynchronous generator, and PMSG with typically voltage and frequency control, and of course different control is used here. So we can call it isolated synchronous generator for variable speed. Prime mover operation has been presented with control such as fuzzy logic based control and SRF control, and different configuration of PMSG based isolated back has been presented, and moreover simulated functions have been typically presented here. So and microgrid based wind and solar array channel mode also presented, and of course the controller based composite sliding mode control as well as the wind parallel operated PMSG also operated like. And then this is the scheme what we talk about: variable speed isolated generation, with the using DFIG as well as with the synchronous generator with the double the converter and used with the different control like. So that was the first part of the wind energy conversion system with the just as the awareness of wind energy generation as well as with the standalone variable speed as well as fixed speed generation. Now we'll be discussing the grid connected wind energy conversion system like. So well, the challenges for grid integration of dispersed wind generation, highly variable wind power injected into the grid, and increased penetration of the wind energy, electrically weak grid network and radial structure, and large error upon explosive distribution line, and heavy reactive power burden brought by the induction generator. So this is typically the scheme that we have infinity. Then we have a typically like a wind energy conversion system with different loads on the system, like a typical scheme. And to come to as a variable with synchronous generator with rotor excitation by Enercon, a turbine with the 6 megawatt, which is the largest wind turbine worldwide installed 2000 speed with the wind variable speed. Like then this is the largest PMSG wind turbine installed 2004 of 5 megawatt by Multipod. Then this is the largest onshore wind farm of 75.5, typically in year 2006, located in USA and installed by Siemens and GE with the different, of course, turbine of different. Then the largest onshore, offshore, virtually in the water, okay, of 166 megawatt with the turbine of 2.3 and installed in 2000, especially in Denmark by Siemens. Then, so these are the some of the installation, unique installation, largest offshore, largest onshore, largest PMSG, largest synchronous generator. Like, so these are only largest one. So now coming to just basic concept, earlier, typically what is used is squirrel cage generator. In 1992, I saw in Okhalamba, Dwarka, in Gujarat, near Porbandar. I mean, the squirrel cage generator with the gearbox with the wind turbine. And there were two machines like a 50 kilowatt for 6 pole with the 1000 RPM and 220 kilowatt with the typically with the 4 pole connected to the grid with the coupled to wind turbine with the gear, and the typical 40 kVR capacitor was there, so that it takes care of this. This is the scheme, of course. I mean, like still typically Siemens is manufacturing, but otherwise, I mean, the only here is a major problem is, of course, you have to use the gear and cage generator with direct soft starter. That is optional capacitor for power factor correction. And the advantage of this is simple and low cost, cheap and low maintenance, and main drawback is the low wind energy conversion efficiency, poor power factor, power fluctuations output, and high mechanical stress on turbine. So this is the largest wind turbine for offshore application with a fixed speed induction generator of wind turbine. The example which I mean the Siemens have installed it, the induction generator of 1500 RPM or 1000 RPM, typically with a two machine, one is 2.3 megawatt squirrel cage machine, another is 400 kilowatt, like 0.4 megawatt machine. So the Siemens is manufacturing such. I mean, they installed in Denmark 2003 in offshore, means in the water, like typically. So coming to variable speed wind energy conversion system with maximum power taking interface to the grid. I mean, this I already mentioned that why we are going to be like a such kind of configuration, because you are able to generate the around 50% more energy from the same wind potential. So coming to like this is typically the what wind energy and power is there. The atmospheric pressure difference accelerate and impart the kinetic energy into the air. And energy conversion machines convert wind energy into electrical or mechanical form, and how power can be extracted. You can calculate from these relations how much power will be extracted according to the wind velocity and area, I mean shaft area, and the density of the typically the air. And this example how much will be from the data if velocity of wind is 10 meter per second, area is 4 meter per meter square, and the density is 1.2 kg per meter square. So from using this relation, you can get the power of 2.4 kilowatt. I mean, from such a small rating system, like, and this is typically a bench limit, like how can. So coming to, in order to operate maximum power of the wind energy conversion system, it's necessary to drive the wind turbine at an optimal rotor speed for particular wind speed, the tip ratio, and to find out maximum operating power point with the, you must have a wind speed, rotor characteristic, and generator characteristic. So this is typically how it goes to like correspond the maximum on these characteristic. But if you can look into this, I mean the normally the cut-in speed is 3 meter per second and maximum speed is 20 meter per second. But here even if you see 5 meter to 20 meter per second, if you even operate at like a 12 meter per second at constant speed at different wind, you will not be able to generate even less than typically around 6 meter per second any power. So you have to operate, if you want to operate maximum power, you have to take peak of these characteristics, which is power versus typically of the wind turbine speed. And there's a generator speed, of course, maybe with the gear also. So that really encourages why we should go for variable speed wind generation. So for optimum operation of wind turbine, rotational speed of the wind rotor should be changed according to the variation of wind speed, and a rate change of the rotor speed is limited. And wind turbine output is interface with the turbine mechanical, aerodynamic, and power, and the rate change of the stored energy. So this is typically the rate change of response time of MPPT algorithm, because it depends on the torque developed by the turbine as well as the inertia, because normally the inertia is quite high, and you can calculate how much is the time is the response like. So there are different methods for wind speed forecasting, which are, becomes important for commitment of the energy form. So this is wind time free data, typically exhibit autocorrelation, which can be defined as the degree of dependence on the pressuring value. And autocorrelation time series models are commonly used for the wind speed prediction. And time series prediction takes an existing series of data and forecast the future value. And of course, people have used the neural network for wind speed prediction. So it's called a neural network because it is a network of interconnected elements, and these elements were acquired by studies of biological, and neural network can train to learn more sequential time pattern. And typically how we can have a time series prediction used to improve MPPT. So you can have a response time and control can be controlled to extract the more energy in future wind speed, and you can adjust the predicted optimum value for synchronize with the optimum actual value. And tracking performance, wind speed, rotor characteristics, generator characteristics are required for track MPPT. And in sensorless strategic prediction value can be used to improve the MPPT tracking performance. And this is how we go for with the wind speed. Then we have a wind turbine speed, and we get from lookup table the reference wind turbine speed, we get the wind speed, and then we have a controller storing the torque on the electrical generator for MPPT, and then pass on to energy conversion system. And we have to keep a optimum rotor speed reference from the or lambda optimum to wind speed divided by rotor radius, and that use the typically for lookup table required for this. This we already talked. For variable wind speed generation, if you are taking with the gear, the squirrel cage induction machine, then you have to use two full rating converters, one for rectification. It operates, the machine can operate in typically in, you can call it in vector control mode. Or you can operate even typically variable vector control or director control for regulating the speed of for maximum power tracking, and then it comes to DC, and from DC you convert from another converter to feed to the grid, the power. So the advantage are optimum power control, 100% speed variability, and smooth grid connection. And of course, disadvantage that your rating of the converter of full rating, and of course will be expensive. This is the typical case with you have a wind turbine with a squirrel cage generator with voltage source converter. Of course, we have a battery on DC link. And for power smoothing of solar as well as wind, and we have a wind solar also with them. So both are connected. This we have a local load. So battery takes care of your intermittency of solar, intermittency of the wind, as well as intermittency of the load. And sometimes grid is not there, still load are committed because you have energy storage as well as generation there, also. And this is typically you can call it the DC link voltage control as well as the for wind power generation, and you have a typically the PV generation, MPPT. So both MPPT are taken care there. And these are typically you can for load compensation. You have a typically the load compensation locally from your grid side control. So the maximum power tracking is taken care by my machine side converter control, like a vacuum control DQ, which you convert into 3-phase currents, and you just have a sense current of wind generator, and then you give the gating signal. So upper are taken care for the grid side current control, which are maintained unity after feeding the local load and the power leveling. Even a fixed power can be fed to the grid, because you already have energy storage. And this is, you can call it islanding, operation, synchronization and islanding. How you do it, so you have to meet the three conditions: the angle. Typically, the voltage should be the same, frequency should be the same, then angle should be the same. Then once all are met, then only close the switch, and the system is able to go from your islanding mode to the well synchronized mode. And this is typically how really, I mean, the grid voltage we have to typically get, because grid voltage maybe you can call it like a unbalanced. So you have to get for synchronization angle as well as frequency for synchronization purpose of the grid as well as for the generator also. And that is typically the system on which this algorithm is operated. So you can see the grid current and grid voltage are balanced sinusoidal, where it's a non-linear load is there, which taken care by the grid side typically grid side converter to take care not only feeding the power to the load and grid, but it also takes care of the compensation of this your local load also. And these are the of course parameters that power quality is improved on the grid side and this is how the TAD is there typically of the load and this is of course for solar generation and this is the performance when you have a solar generation change and when you change load removal load application and battery disconnection. So all the cases are taken here and system work very well without any much problem. Like when load is removed, load is brought back in a stellar mode, aligning mode, and it works without any much problem because battery there. It takes care of intermittency of the load as well as intermittency of the generator. And typically the synchronization here. You can see the grid appear after few cycle of grid appearance and it synchronizes, and once synchronizes you can exchange the power from the grid and these are typically like when the solar generation go down, okay, and how the power flow changes then of course with the skull cage generator with the gear people have used the matrix converter because it is capable of generating like a variable two frequency on both the sides. So grid generator side the variable frequency and grid side is the fixed frequency, but with the matrix converter you can maintain the unity power factor on the grid side also along with the sinusoidal current and motor current also can be controlled by matrix generator current also. So advantage is the elimination of DC link reactive elements and compact solution yield high power and smooth grid connection low voltage. But of course it couldn't go to matrix converter are not available in high rating, so it couldn't go to very high rating also. Of course complex control and technology yet to mature. Then of course people use with this wind turbine with this skull cage generator with the gear the current source converter. So you can say pendulum current source converter with the GTO. And of course, the converter current are discontinuous, but the capacitor you have to put on both the side of converter with the pendulum current source rectifier and pendulum current source inverter. And you have a capacitor which makes the current sinusoidal smooth and the balance and sinusoidal. And grid side can be unity. But the disadvantage on DC link, you are putting an inductor which are costly, bulky, and noisy. Moreover, the GTO cannot operate at high switching frequency, so that causes the capacitor value to increase a little higher on that. And these are typically the control for what you can call it MPPT on the turbine side, and this is typically the control on the power flow from the DC link to the grid the proper MPPT control. Now coming to the a DFIG, for practical application, GE had already installed in Canada even in W-fed induction rate of 1.5 megawatt turbine by GE Energy in a wind farm of 109.5 megawatt, and then that was onshore. This is offshore. Vestas has developed 2 megawatt wind turbine, put it W-fed generation first offshore wind in farm in UK using DFIG. And RE Power is also manufacturing 5 megawatt DFIG, largest DFIG that time in Scottish Sea. Then this is like what your DFIG. So which already mentioned that DFIG with the grid connected system for around 75% many industry are manufacturing this DFIG. And here you can see, this system, of course, we have to use the gear. Even in case of your UK, we have a same frequency, and the generator have to work from 1000 RPM to 2000 RPM. So the base speed is considered 1500 RPM sequence speed. The major benefit of DFIG, one is the rotor converter rating is hardly low, as it is given mentioned here, around 25 to 30%. And you can call it like around 120% power is generated from stator side and 30% from rotor side. So the DFIG is capable of generating 150% rating compared to rating. If you have you can take a turbine of 1.5 megawatt. If you are taking a DFIG of 1 megawatt, it can generate 1.5 megawatt. But the losses, since you are not increasing the voltage frequency either from stator or rotor, so losses does not exceed more than the losses under rated condition. The output power increase 150%, but your losses are corresponding to the rated, and that really, you can call it like interesting feature that efficiency supersede from the compared to the even your synchronous generator. The another benefit of this that you are varying the speed from 70% to 130%. If you because the wind speed generation is proportional to the cube of the speed, so 0.7 cube is like a typically around 0.34, hardly. I mean like a and the cube of 1.3 is 2.12. So you can take the ratio of your 0.34 divided by 2.15. This is hardly a 16, 17, 15%. That is the only losses. So, and 2.12, if you are taking 2 megawatt, then it will be only like a 340. So that will be the losses. So it suits very well. On DFIG suits very well. And this is the only generator from which the around 120% power can be directly connected fed to the grid. Even your turbine is operating at variable speed as well as generator rotor speed is also operating under variable speed. Like so, the rotor converter is hardly of 25 to 30%. That's another. So, power electronics rating is cost low. Moreover, the rotor voltage is also low. So, low voltage converter, low frequency converter order of even in megawatt rating, you only have a 1.8 kilohertz switching frequency of these converter. Like so, DFIG have a specific benefit for wind power generation. The overall advantage of this DFIG system is reduced converter cost as the converter rating is hardly 25 to 30% of total system power rating, and improved efficiency due to reduced losses in the power electronics converter, and suitable for high power application including reset advantage in offshore installation, and it has gone up to typically order of around 8 megawatt single unit, and bidirectional power flow of reactive power, and a high rate rise of through capability during network distance and flexible 4-quadrant operation with precise control. Another important aspect I have forgotten to tell you that if you feed the reactive power from the rotor side, it's only the slip times your reactive power fed from the stator. So that's the reason we feed the reactive power from rotor side. I mean, like, of course, that is also in synchronous machine also same thing. In synchronous machine also we feed the reactive power from the rotor side, but that's only the DC, so you feed only the losses of winding. So same concept here, it is on the rotor side. If you feed the reactive power, it's a slip times the reactive power which are so otherwise fed to be from stator side also. So these are with this benefit. I mean, this machine supersede all the machine as far as the wind power generation is concerned, this DFIG. And that's the reason people about 1980 to 2000, people have forgotten to even this wound rotor induction machine in 2000 G brought this technology DFIG for wind application. And well, it's by 75% industry are manufacturing this system. I mean, like with the DFIG, like I mean, typically like. So the other benefit of this generation in that converter rating is quite low. In this case, only 25 to 30%. I mean, it's not much. So what is the basic principle of operation of it? Like the frequency of grid voltage always maintained constant irrespective of the wind speed and rotor speed of the typically of your this DFIG based wind energy conversion system. And by using the converter to control the rotor current, it is possible to have adjust active and reactive power fed to the grid from the stator independently, because you have a grid side converter which can have even a additional reactive power it can generate for the grid system also. That is another benefit of this system, like I mean of DFIG when connected to the grid, like I mean. So at subsynchronous speed, the stator is generating the power, but the part of this is fed back to the rotor. At supersynchronous speed, both rotor and stator are producing the power to the grid. And that's why I was talking about, like at maximum speed, 30% power is generated from rotor and around 120% power is generated from the stator. So current rating of rotor converter is defined by the, typically you can call it the maximum active current required for the torque production, and the maximum reactive current required by magnetizing the machine. And if all magnetizing current supplied by the rotor winding, the stator will only have a torque current, so the unity power factor operation on the stator side. So in wind driven DFI, the primary control objective are to maximize the power capture in sub-rated condition, maximum power trend taking, and limit the rotor speed in rated region, and control power factor at all the time to unity on state side. The responsibility of your rotor converter is control of torque and flux of the machine, control of the torque for maximum power tracking, and the control of flux to have a unity power factor on stator and a reactive power flow of the machine, and responsible for MPPT. And grid side converter maintain the DC link voltage constant irrespective of the region of operation, whether it is taking the power rotor power flow, whether it go to the rotor or it is taken from the rotor, and ensure the UPF in either direction of power flow. And inner current loop, you will surprise that there are around 8 PI controller used in this system. So inner current loop control the rotor current, and outer loop we already talked about the maximum power tracking as well as reactive current. And outer loop is the control electromagnetic torque for maximum power tracking, and stator active power for and the total active power output is rotor and air gap electromagnetic and the rotor speed we control. So this is typically the control block diagram of this DFIG. We have a rotor speed which have a maximum power tracking. We are getting from typically torque producing component, from the speed control, and from reactive power, which you can have even 0 for stator, that is for stator. So you can have a rotor torque flux producing component, so that give you the rotor current. So we have a 2 PI controller there, and 2 PI controller. Then we are converting to ABC rotor current into DQ, and we have again current regulator into DQ, which we are converting back after current controller into from this equation into DQ voltage, and from DQ voltage from the transformation we are converting from inverse power transformation we are able to convert to ABC, and which have a voltage control of VSI, because we are operating this VSI at low frequency of only of 1.8 kilohertz like so voltage control is there. So what are the observations for this DFI? Active power balance responsible for MPPT always made equal to the available maximum power point input, treatment form speed, and power assistant circuit are also considered, and reactive power reference, active power reference with the desired power factor of stator to unity. The external flux reference, the rotor current variation effect on. So inner control loop is the rotor current, outer loop is the DC link voltage control for the grid side converter control, and from the grid, and rotor power flow should be coordinated with the, and they typically your grid side converter control, that we control the DC link voltage, which gives the active power, and reactive power you can of course have for the grid side, and we are getting DQ component, and from sensing the grid side current converter current we are getting DQ, and then you have a current controller, DQ current controller equation are given here for all 4 PI controller for grid side current controller, grid side control, and these are the 4 PI controller for road side grid current control. So there are like 8 PI controller used in DFIG. This is about how you are having a total reactive power controller. And this is the block diagram for entire control. This your DFIG connected to the grid system with both the roadside control. And this is the simulator performance, of course, below subsynchronous speed, where you can have a rotor current at the 4th waveform at slip frequency, and you can see that the stator reactive power is maintained 0. Like here, and DC link voltage is also regulated. And then this is for the corresponding to the super synchronous speed, where the you can see slip frequency again of the rotor current, and again the reactive power on the grid is maintained, or stator is maintained 0. DC link voltage is regulated corresponding to super synchronous speed, and this is at synchronous speed. You can see the rotor currents are DC, and again the reactive power is maintained 0 at the stator side, and then your DC link voltage is also regulated. So you can see that it works in all the subsynchronous speed range, super synchronous speed, as well as synchronous speed. Also it works as like a synchronous generator like. And this is the typically you can call it, if you can use, that's exactly what I was mentioned, that you can use the DFIG 1.5 megawatt for 2 megawatt wind energy conversion system. That the efficiency is improved compared to if you take a 2 megawatt DFIG with 2 megawatt wind conversion system. And these are of course the losses in 2 different systems also. And of course there are other control schemes that you can have active and reactive power control, that called power control like that also. These are the equation for PI control, typically for the torque producing component for reactive power control, and typically the torque speed control output as a torque control, then the rotor current D and Q current with the give the DC link voltage. Why DI control? Because all are the DC quantity. That's the reason we take SRF control theory for this DFIG control. And these are grid side converter control with the DC link voltage control, and this is typically your reactive power to maintain 0. So you have again DQ and convert into ABC by reverse path transformation. Again here PI controller are used because it DQ DC quantity under steady state, and we maintain maximum power tracking corresponding to at peak power at different variable speed also for man. That is the reason why we have. And this is of course the performance at different wind velocity. I mean like 6 meter per second, 12 meter per second, and then typically even variation from 6 meter to 12 meter per second dynamics how it goes. And this is interesting, typically the comparison of stator and rotor power, how it is going to be, I mean, to the grid, like, I mean, and you can say lower speed is goes negative from the rotor side, and the different power, stator power, grid power, and so. And this is interesting story which I ask my student to do it, that if we take a fixed speed, squirrel cage induction generator, and you generate this much. We took a one location in Jacoy in Tamil Nadu and look into the wind speed variation, that for how many hours, what is the wind velocity. And we found if you take a variable speed like a DFIG, you are able to generate this much kilowatt hour, 10,950 kilowatt hour. And if you take a typically squirrel cage generator with the fixed speed, you are not able to generate below like around 6 meter per second. But here you are able to generate only 7,180 kilowatt hours. So 50% more energy generated from variable speed. That's the benefit why we use the variable speed. So this also we prove analytically from taking a data from this and and simulating with the actual system also. So this is typically what I was talking about, that okay, this give you like a grid interactive wind turbine. So this here this converter can be used even for load compensation also, along with the your power fed to the grid also, like so that's typically which we were talking about. And this is like a variation how you can have a next, typically the power generation corresponding to that, and reactive power sharing, like for DFIG, and where we should operate for reactive power sharing of the DFIG, like for different conditions. And you can clearly see that part of the reactive power, that is one of our student did that, okay, reactive power should be shared for the machine from storage as well as for rotor for minimum losses also, and wind speed varying and feeding local non-linear load. The rotor side converter is capable of compensating, but your generator current and grid current maintains sinusoidal and balance and unit power. So this is a experimental setup, from which one of my students did with virtually the one converter with battery, and it give a better performance. That okay, if you are using a battery typically as a grid connect, so you can have a power leveling on the grid side also. So these are the results corresponding to that. And TID of the grid current also maintain quite low, as well as voltage is also maintained. So performance under that condition and under wind velocity variation also it works very well. Even you can feed the constant power to the grid like under that condition also. And then the below synchronous speed to upper synchronous, upper to lower synchronous speed, how it is. All these are experimental result with the TFIG with the single converter like so. And of course you use the direct power control also for the same purpose. Then look into sensorless control of this your DFIG, typically. And these are the experimental result with sensorless control. So estimation, these are the typically sine theta, cosine theta are estimated by voltage and current sensing, and work well with the sensorless control with the sector for direct power control. As you have a DTC in induction motor, here we have a direct power control. It's a reactive and active power are controlled directly from this algorithm. And for the change of the power level also, you can control the power from stator in this system. And then wind speed variation also, and grid power is maintained constant in that case, like under wind speed variation. Then of course another system that you can take a PMSC without gear, and but you require a full scale converter in that case. So that's many industry are manufacturing. That the benefit of course is full range, but the disadvantage is that the inverter rating, entire power is processed through both converters. So converter rating is more than 200%, where DFIG converter rating was hardly 60% of the power what you are generating the power to the grid. Like, so all the, and you can just see how PMSC, like you have a, again with the our student have built up sensor control for PMSC with maximum power tracking and putting to the typically to the grid with the load compensation from grid side converter. Of course, with the solar generation also in this system, like also. So this is the control algorithm, and this is the practical system how it is in the installation, and these are the results under wind variation. Still the, you can call it the grid current are maintained balance and sinusoidal, or wind generation also currents are maintained balance and sinusoidal. Like, whether it is a wind variation or it is a load variation, you can say load removal, load applications, how it is the performance is I mean, not affected. I mean, typically grid current but remain balanced and so. Then of course for lower rating, people have used like it with the PMSC diode rectifier, it's BLDC, and then the thyristor converter to feed power to the grid like also. And of course, then because thyristor converter have a power quality problem, so it's taken as a voltage source converter with diode rectifier, and voltage source converter of course can have a unity power factor sinusoidal current feeding to the grid. These are normally used for lower rating like then of course the after that is a boost converter for maximum power tracking, so that DC link voltage is constant, and from voltage source converter you can put to the grid like also. So this is another PMSG with both the converters. And of course with the single stage gear if it is required, and these are operated in vector control mode both the and unit power factor on the grid side also. And this is of course current source converter we already talked earlier also with the pendulum control, but the problem is with this the GTU cannot be operated with the high frequency, so capacitor size increases on both the sides. Of course that's also have a stability issue like, and moreover inductor. Of course, voltage source converter have taken a lead in the technology, and this is to reduce the cost. In place of 2 lag, you can have a 3 lag with PMSG, like or maximum power. And this is typically kind of, you can call it the summarization how the rating enhancement have been there with the large rating. You people start using a multi-level also in the for wind energy conversion system. So it's a 3-level. You can just see permanent synchronous generator with the 3-level, then DC link, and then grid side also 3-level. The ABB, the typically IGCT converters is used for this medium voltage. For neutral point clamp converter for wind application. Like typically the then 3-level GTO. Typically phase lag control for, and then multiple converter in parallel to increase the rating for the 2-level converters like. And the typical example of NR-con, what they are using, simple synchronous machine with the rectification, and after that they are using converter to increase the rating in parallel, like also to enhance the rating. The NR-con system is cost effective. Synchronous generator you can use simple kind of rectifier and then followed by it. So that's about typically synchronous generator. Our student also use, but we use in vector control, machine side converter and grid side converter. And of course with the battery and DC link, so that you can discharge constant power to the grid and compensate the load also with the advanced control technique with the unity power factor operation of this, like with the MPV and experimental performance with sensorless control, like a position is also estimated for the control of the synchronous generator, and power quality is also improved on the grid side with the almost TAD of even an only load TAD is quite high, but the TAG maintained quite low on the grid side, and then the effect of the wind variation, solar variation, load variation, load nonlinearity, all are taken care in these results. Like also, and this you can clearly see when the TAD of only 2.3% of the grid current is maintained when the load TAD was current TAD was quite high. Like then of course it's a permanent brushless DC generator which are used for very low power. There is a concept coming vertical turbine of very low rating. Our institute in the applied mechanics they are using vertical turbine of as a grid for, and they say power density from the same area can be increased, but we need the lower rating turbine of 1 to 5 kilowatt only. That's the reason we have a micro, you can call it the micro turbine kind of concept for wind power, and then we have to use BLDC with the very cost effective. So BLDC with the boost converter with the MPPT can be used in this, and along with the here the solar and battery charging infrastructure to put to the grid, like our different these use, because this kind of system are used for going to be used for charging infrastructure with the microgrid concept, like so these are the of course the configuration in islanding mode as well as synchronized mode, and with the grid control in the different fashion, like operating in different mode, and you can feed the local load also as well as. Then of course our student have used recently the synchronous reluctance machine. This machine is very recently appear from ABB as well as Siemens. They are start manufacturing from from 1 kilowatt, and they are going typically order of typically more than 300 kilowatt machine, and this machine is much efficient than your squirrel cage machine because rotor losses are completely well out, like so here also converter with the vector control is operated for maximum power tracking, and then the grid side converter with load composition and operated even with the local load in islanding mode also with sensorless control. This typically with the power observer, and these are typically experimental with the I mean, in islanding mode, only 1.89% TAD with when it's feeding quite highly now also. And when the wind variation, because battery is there, so it takes care of that. Load change, load removal, load application, all conditions are experimentally observed and it works very well. And of course, with the battery, then if grid is not there, you can commit the load and intermittency of winter generation, load generation, as well as the grid intermittency is taken care by the battery in this system, like of wind generation. And that is about, I mean, when that is connected to the grid and feeding only load, but the TAD of the grid current is only 3.7%. And when the wind velocity is changing, it works very well without any interruption. When load removal and load application performance is also found quite satisfactory in these all situations. Here, of course, we put the battery with the buck boost converter so that you can take optimal rating of the battery, like I mean, this operating islanding mode as well as in synchronized mode also. Typically, like I mean, so these are the, and this is coming to as a summary that which I already mentioned, that the people are using squirrel cage fixed speed by especially Siemens, Ecotania and Mitsubishi and Suzlon. They are manufacturing the fixed speed, and of course DFI is manufactured by Nordex, Ecotania, Gamesa, RE Power, Vestas, and GE. They are manufacturing DFIG, and PMSC is manufactured, of course, Multipart, GE and Mitsubishi, and wound rotor synchronous motor by Enercon, and cage generator by Siemens, which I mentioned it. And of course, summary of existing control algorithm. Of course, we can talk about how to use for MPPT depending upon the converter. I mean, which converter you are using. MPPT control with variable speed is there in all the configuration also, and according to the current control line. And of course, we talk about off-grid synchronous generator, then PMLDC for lower rating, then the wind turbine synchronous reluctance generator, and then, of course, these are the typically some of the references. There are around 40 books in wind power generation. I mean, some are listed, the list here, around 40. Typically, I saw 40 books up, and then these are some of the publication form which we, and of course, our student work like. So thank you very much. I mean, like, and back to you. If any questions
Thank you,
there, I
sir.
will be happy to answer.
So without taking much of your time, I request all the participants, if you have any queries, please. You can put in chat box as well.
So it is online, na?
Yes, sir. Yes, sir.
I'm not very sure how many are present.
Okay, sir.
Anyhow, you can, like,
Oh.
if somebody have some doubt, no problem. Or can
Okay,
give the
okay.
email also, there is no issue, okay?
Okay, sir. Okay, sir. Sir, with your permission,
me, sir.
we, yes.
Hello.
Yes.
Yeah.
Sir,
Go ahead.
sir, my name is Gaurav Yadav. Sir, I want to ask about the noise. Sir, that so this is also a somewhat issue in this wind energy conversion system. So it might be take more. Uh, uh, no, I want to ask that should we take there is something would be done about this about the noise that is a issue in this, or
No,
it is not much of concern.
no, there are two important aspects. One is the wind turbine is not very close to your locality, provided you have some rooftop small rating. And another is the all the machine which we mentioned about it, they don't have any torque ripple. Okay. So from electrical side, we don't have any noise. If there is a mechanical side, because there is a motion, that noise we cannot control because we have to operate for maximum power at particular speed. Are you able to follow like? So mechanical
sir.
system noise we cannot control, but electrical noise is not certainly there in this system. Are you able to follow like I mean?
Okay,
So
sir.
that is I can answer partially. I hope it partially
Okay.
satisfy your query like.
Okay. Sir, one more thing that if any fault occur when it is grid connected system, so as we are having a continuous power supply, so
There are
when there is a fault.
no, there are lot of technique like I mean typically there is a supposed to be even in DFI there is a crowbar. Okay, so you have to certainly feed the energy to that like okay when there is a
Okay, sir.
fault on the grid like. So there are a lot of literature available on write-through capability as well as the fault analysis on these. So people developed the concept even 10 years back. I was just talking in a conference,
Okay, sir.
in US conference. So I mean, actual system takes care of those fault into
Oh,
account, like okay.
okay, sir.
Mm.
Okay, sir. Thank you, sir. Thank you.
Okay, you are welcome. Like.
Yeah, any more queries, participants? Sir, with your permission, can we go ahead with our...
Sure. So can
Yeah.
I leave? Thank you very much, anyhow.
Sir, just a small vote of thanks for you, sir, please.
Oh, sure, sure. No problem. Thank you.
Thank you, sir, for giving us an opportunity to learn from you about power converters used in wind energy conversion systems. Sir, you have given a lot of information at our session. Your session was very interesting, sir. And more importantly, your inputs will greatly help researchers and students who are carrying out or planning to do research on wind energy conversion systems. Thank you, sir, for sparing us a valuable time with us in spite of a busy schedule. Thank you so much, sir.
Okay, thank you very much, Amin. Like, okay, thank you. Bye. Like, all the best.
Thank you. Thank you.
Okay.
All the participants, I will share the link for the feedback session, feedback forms and attendance sheet in mail as well as in your WhatsApp group also.
Thank you, Anil.
Hello.
Thank you so much.
Thank you, sir. Thank you a lot.
Thank you, sir.
So should we wind up
Okay.
the session?
Yeah, we can leave the session, sir.
Okay, thank you, sir.
Excuse me, sir.
Yes.
Sir, shall we get the videos for the previous session, sir?
Yeah, I think yeah, you may get the I don't have the videos. Probably if there is some content that can be shared, I will inform you about that. I'll
Yes,
confirm you about that.
The second session, sir, importantly, the second session was very useful for me, I think. So I need that information, sir.
Okay.
If it is
Okay.
possible,
Sir,
then
yeah, just a second. Sir is saying something.
It will
Please listen.
uploaded in YouTube also. Okay, you can download from there. You can see from there also.
okay,
This
sir.
video
YouTube link was given only for the inauguration function, sir. But we didn't get the.
that link we will upload later on. Okay.
Oh,
You
okay,
can
sir. Then
access
it will
it from
be.
there.
Thank you,
Okay.
sir. Thank you so
Don't
much.
worry.
Yes, sir. Okay, sir. Thank you, sir.
Okay. Sir, can we end up the meeting, sir? Minar, sir.
Hello, Anil, sir.
Sir. Okay.
Should we end up now?
Yeah, we can end up. Yes.
Okay.